Καλημέρα.
Dear participants, we will commence in 10 minutes from now. 10 minutes from now, please. Thank you.
Pronto?
So dear participants, dear colleagues, good morning, good afternoon, good evening, depending on the time zone from which you are following us. My name is Pier Antonios Papazoglou. I am from the Climate and Atmosphere Research Center of Excellence at the Cyprus Institute, and I would like to warmly welcome you in our Climate and Atmosphere Research and Innovation in the Eastern Mediterranean and Middle East virtual workshop. Before I hold for a few minutes the floor for technicalities and logistics, I would like to, without further ado, invite to the virtual podium the director of the Climate and Atmosphere Research Center of Excellence, Professor Jean Siar, for a short welcome and introduction, and then the floor will be back to me for a few technicalities and logistics. Professor Siar, the virtual floor is yours.
Good morning. I hope you can see properly my screen. Sharon, the news, can you please confirm?
I do confirm, I can see your screen.
Okay.
I can also see on the top right, I can also see your control panel. Merci.
So, good morning, everybody, for this pre-conference workshop on the climate and atmosphere. This workshop is a two-day workshop. It's happening before our climate change international conference that will take place on Wednesday and Thursday online, and you have the web link on this front page. This workshop is organized in the framework of the MCARE project and the climate change initiative of the government of Cyprus with the support of the European Commission. This workshop is hosted by the Climate Atmosphere Research Center at the Cyprus Institute, which research center I'm responsible for and takes care of environmental observations, prediction, and evaluate regional impacts on air pollution and climate change. So this workshop, as mentioned, is taking place before the conference. So you will see on this website of the conference here more information, and in particular the program that I invite all of you to look at with the prestigious speakers all along the 2 days of the conference. Our workshop, if you go on the website of the workshop, you will see the program, so the program of today and tomorrow, but also the program, the abstracts of the program, so that you can get also some memory out of it. So please don't hesitate to go and visit our website and to get the updated program that will take place today and tomorrow. In terms of participants, I'm glad to inform you that more than 200 participants have registered to this workshop, and from 34 different countries. And the Eastern Med and Middle East participants are widely represented here with 14 countries and 174 participants, but we also will have some participants from Europe, America, Africa, and Asia. All the components of the quadruple helix are represented here. We have participants from the higher education research organization, from the governments, third sector, private sector, and others. A visual of how many participants for the region, with of course a lot of participants from Cyprus, but also a lot from Greece, from Egypt, as well as colleagues from the Gulf. So the objective of this workshop today and tomorrow is to bring together researchers from the Eastern Mediterranean and the Middle East to present and discuss the latest scientific challenges and the findings they have made on regional air pollution and climate change. This workshop aims to strengthen our regional collaboration and better share our knowledge, build national capacity with the objective to better adapt and mitigate. The workshop topics that will be presented today and tomorrow cover a broad range of scientific activities ranging from climate change and weather extremes, atmospheric dust, air pollution sources and impacts, greenhouse gases and remote sensing observations, atmosphere and climate modeling and prediction, new instrumentation research infrastructure, and international networks and regional initiatives, and finally, education and training opportunities. So you will have the chance during these 2 days to go all these different topics with the presentation that are relevant to our region. Now, the objective beyond this workshop is hopefully to make this event and turn it into an annual scientific workshop, similar to other international conference that takes place in Europe or in the Northern America, and have it organized in different countries or cities in the region and in hybrid mode with online, but also hopefully physical presence. The objective also beyond this workshop is through the participants who have been engaged today to keep them engaged through a virtual platform, a web forum that will streamline scientific dissemination, discussion, communication, research call, PhD opportunities. With this, I will not take too much of your time, and I will wish you a very nice workshop for today and tomorrow. Thank you very much.
Thank you very much, Professor Sia. Now, like I've said, just before giving the floor to the chair of the first session, I would like to, first of all, sincerely thank the colleagues who have made the workshop practically and organically possible and feasible. And this is Angelos Alexandrou from the Cyprus Institute's IT support, but also our own MA Care and Care C colleagues, Project Officer Andri Haralambous and the Communications Coordinator, Mrs. Marina Papageorgiou. But of course, I would also like to very importantly thank you all for joining us today and hopefully tomorrow as well. Your participation is what makes this workshop important for its deliberations and for the results that it will provide to the scientific and to the policy-making community. After thanking you, I would also like to invite you to kindly take note of the following technicalities and logistics. First and foremost, since we do live in a virtual and electronic era, please remember to use your social media, and please remember to use the following hashtag, which is hashtag EMME4 with the number climate. So hashtag EMME for climate is for all your posts, tweets, likes, etc. on your social media platforms that you are using. Now, to more important technicalities. Each session will have a chair. The chair will, of course, be responsible for kindly introducing the sequence of speakers. Also for relatively keeping the time, but please kindly note that you do have a strict timekeeper, which is unfortunately my role. And I also have an even stricter timekeeper, which keeps me in check. So overall, we will try to have a very nicely timed workshop because it is compact and because it is virtual. So we do need to take care of our timing. We will remind speakers at 5 minutes and 2 minutes. And then we will kindly ask to wrap up. So please also time yourselves. Invited speakers and oral presenters are kindly invited to open their cameras and their microphones only when presenting. So please keep that in mind as well. The allocated time for each presenter is 15 minutes for invited speakers, followed by 5 minutes of Q&A. And for oral presenters, it is 7 minutes, followed by 3 minutes Q&A. Later on, we will provide also technicalities for VPICO presentations. Other than that, I would like to again thank you all. I would like to welcome you again. And without further ado, I would like to give the floor to Assistant Professor Theo Christoudias from the Climate and Atmosphere Research Center of Excellence and the Environmental Predictions Department to kindly chair the first session, which is on atmospheric modeling and prediction. Professor Christoudias, the floor and the chair is yours, please.
Thank you, Pierre Antonios, and good morning, everyone. I would also like to thank Jean for his introduction. So, as Pierre Antonios mentioned, this first session is on atmospheric modeling and prediction. And I have the pleasure to invite an esteemed colleague, Professor Maria Kanakidou, to open the proceedings of the workshop with an invited talk titled Human-Driven Changes in Atmospheric Deposition of Nutrients to the Ecosystems. So, Professor Kanakidou, the floor is yours.
Yeah, thank you very much. It's a pleasure to have this opportunity to share with you my thoughts and my results. I'm not sure you can see my slides.
We can see your screen,
Professor Kanakidou.
You cannot see. Do you see now the slides?
Now we can see. Yeah, now we can see the slides. Thank you.
Yes, perfectly fine. Also from here, please, please carry on.
I can also open my camera so you can see me if it works. Yes, but no. Okay. So. Sorry for that. I don't know how to minimize this one, but doesn't matter. You can.
I will kindly ask all other participants to please keep their microphones closed. Thank you. Professor Kanakidou, the floor is yours again.
Yeah, thank you very much, and apologize for not being able to make disappear this one, but you will see it like that, I think. So I would like again to thank the organizers for giving me the opportunity to share with me my thoughts about the importance of atmospheric deposition of nutrients to ecosystems. We know that atmosphere is a major corridor for transporting various elements, material and energy also from land to ocean. And with this material, nutrients are a major component. The anthropogenic emissions have changed the flow of nutrient fluxes from the atmosphere to the ecosystems quite a lot. However, there are large uncertainties about how much this has changed and what are the impacts on ecosystems, food and climate. And here I would like to attract your attention to the fact that this indirect effect of air pollution to climate through the changes in the biogeochemical cycles of nutrients has been only recently started getting into account in the IPCC reports. Why that? Because it's rather complex. There are thresholds on nutrient levels that affect the ecosystem functioning. Little is beneficial. Here you see an example from land, where we can see the additions of nitrogen to the ecosystems, forested ecosystems in Europe, how they affect the growth. Adding more and more nitrogen, it goes to a growth of optimal growth, and then adding further, then you have a reduction of growth. When we look at the biodiversity, the species inside an ecosystem, then you have an increase in the beginning, and then you just have a reduction afterwards. So little is beneficial, too much is harmful. And also thresholds and limitations we can see also in the oceanic ecosystems. For instance, on this slide, it's overlaid at the top of phosphate concentrations in the seawater. There are colored circles that show what is missing from the ocean system in terms of nutrients or elements to be able to go full speed on ecosystem growth, let's say. And we can see in the Mediterranean region, for instance, it's green, which is nitrogen, and black, which is phosphorus. So the system in the Mediterranean is somehow controlled by the inputs of nitrogen and phosphorus and the sources of them into the oceanic system. Also, if we look on what atmospheric deposition brings to the sea, on this slide you can see the ratio of nitrogen to phosphorus into the seawater by blue. It's the ratio in the seawater from measurements into the seawater, which goes from 16:1 to the west, from the West Mediterranean to 28:1 in the East Mediterranean. So this ratio increases towards the east, and the 16:1 is the typical Redfield ratio, while the 18 to 28:1 is higher than that. It shows that we have less phosphorus that we would like to have for a typical ecosystem functioning. And with red, you can see the nitrogen to phosphorus ratio in the deposition. And there we can nicely see that this also increases from the west to the east. And in the East Mediterranean, it's pretty high. So there is a hypothesis that is quite a lot supported by models also, that this atmospheric deposition is what is leading to this anomalous nitrogen to phosphorus ratio into the seawater. So the Mediterranean is an oligotrophic marine environment, which also shows the same gradient, opposite this time. We have seen that nitrogen to phosphorus ratio increased towards the east. And here we can see that chlorophyll as a kind of a proxy for the marine biological activity. Decreases also towards the east. So the East Mediterranean, where we care about, is a rather oligotrophic area. So it's important to see what is getting into the sea. And it's also a particular place because we have significant interactions between natural and anthropogenic emissions. As it's a crossroad of air masses coming from different areas, with bringing different material to the area. It's a place where you can nicely study and see the effect of mixing of dust with pollutants and also biogenic emissions that are around. This mixing of dust with pollutants also implies that dust particles are chemically processed in the atmosphere by multiphase chemistry, which can be acid proton promoted reactions or can be ligand promoted reactions. And all of them will mobilize iron and phosphorus from the insoluble core dust particle to a soluble version that will go into the sea as easily taken by the ecosystem form. And indeed, atmospheric acidity is important for the nutrients forms that are available to the ocean, but also to the other ecosystems, because the emissions of various nutrients or compounds that carry nutrients to the atmosphere goes through atmospheric processing in an acidic environment. Then the deposition of the forms of nutrients is important. Questions we have is, what is the strength of this deposition and what is the distribution? Where is deposited? Where is, for instance, the impact of dust deposition in the Mediterranean, where it happens? And are organic forms of nutrients important? How important they are? And obviously, what is the impact of atmospheric acidity and of human activities into this how we treat it, how we answer those questions. First, we answer them with global three-dimensional chemistry transport model simulations of atmospheric deposition of nutrients. This is a model that we developed at the university here, all the chemistry part, in particular the nutrients part, where we have all the three important nutrients, nitrogen, iron, and phosphorus, coupled together in one system. And we also have a comprehensive organic carbon chemistry, which allows us to simulate the organic fraction of nutrients by using the nitrogen to carbon and phosphorus to carbon ratio in the different components. And also, in that case, we can nicely simulate organic nitrogen and inorganic species, the inorganic and organic phosphorus, as well as iron and its organic complexes into the environment. And I will just show you one slide from the global modeling findings, because it's very relevant to the regional also scale. And first, performing the first organic nitrogen global modeling study, we found that in terms of deposition, we found that this organic nitrogen source is increasing the total nitrogen deposition by 20%. And it's also by 40% anthropogenic, while on a total organic nitrogen deposition is 20 to 25% of total nitrogen deposition. We also see on this dissolved organic nitrogen annual deposition maps the anthropogenic contributions. We see the biomass burning, but also some bioaerosol contribution, and we also see the marine source contribution here. We concluded also from that study that bioaerosols are important source of organic nitrogen, and we also found the same and even more important contribution of bioaerosols to the soluble organic phosphorus compared to the total soluble phosphorus. We know by far that dust is the major source of phosphorus in the atmosphere, but this phosphorus is insoluble. So the bioaerosols come to add a significant amount of soluble organic or bioavailable organic phosphorus to the system. And the last key finding has to do with the contribution of combustion to dissolved iron. And this is a result that has been consolidated within the GESAMP group of WMO, where different models contributed to these publications, and found that indeed the combustion contributes quite a lot to the dissolved iron deposition. And we see here the maximum over various areas, but also we have something like 60 to 70% downwind of combustion areas over the ocean. So it's an important contributor to the combustion source.
5 minutes, please. 5 minutes.
Yeah, thank you. On this slide, I focus on the Mediterranean, showing the dissolved nitrogen, phosphorus, and iron, as calculated again by the model and somehow interpolated to the region. The most important here is that we have different patterns. So where we have the maximum of phosphorus deposition, we don't have the maximum of nitrogen deposition. And to the right, we see the comparison of the model results with observation that is guiding where we need to look in more detail for improvements. So we have a comparison of deposition at Phenocalea and for oxidized nitrogen, reduced and organic nitrogen, for iron, and also for dissolved organic phosphorus and total soluble phosphorus in Perpignan and Phenocalea. And what is the conclusion of those results? We have done two simulations. One red is the base case, and the green is a simulation where we increased by 14 times the soluble phosphorus, in particular the organic phosphorus flux, and also we increased the soluble iron by 2.5 times. So we see that these fluxes have to be higher than what are actually into the models. And our nutrient flux estimates for the Mediterranean Sea is the first column here for nitrogen, for phosphorus, soluble phosphorus and soluble iron, and we can see that they fit within the range of uncertainty into the region. But we have also some higher up estimates, which are always into the range of earlier estimates. To show now, go to the human-driven changes. We've done a simulation for present day and for past, only changing the emissions. We did not change the dust emissions, so those are biased toward the anthropogenic emissions of various components. And we found that in general the emissions, the fluxes, the deposition fluxes has increased from the past to present, from nitrogen, for phosphorus and for iron, and they are expected to decrease in the future. And here you see the multiplication factors for that. It's interesting to see here that the dissolved inorganic nitrogen shows a smaller decrease than others in the future, and this is because of the ammonia emissions that are not still not strongly regulated coming from agriculture. So those we expect that will have impact on ecosystems. We have done a very simple 1D study in the past using the fluxes of dissolved inorganic phosphorus, dissolved inorganic nitrogen into the sea as measured. We put it in one-dimensional model that has the physics into the upper layer, and also the simple ecosystem functioning representation. And we found that without atmospheric deposition, the nitrogen to phosphorus ratio goes down to Redfield ratio, while with the atmospheric deposition, this stabilizes to what roughly we see in the area. So this is a good point that atmospheric deposition is controlling what we see into the ocean. And also we found that dissolved inorganic phosphorus sustains about half of the new production into the area, accounting for a kind of remineralization of phosphorus into the sea, and found an important role for bacteria, which contribute about 40% of the carbon is recycled by bacteria. So I will not show probably those estimates from the deposition fluxes impact, but we can evaluate the nitrogen, the impact on nitrogen fixation and on carbon fixation with the results of our model and simple calculations. We found that dissolved nitrogen deposition can account for half of the new primary production into the environment. Phosphorus is not able, as the deposition of phosphorus is not able to support this primary production, but remineralization inside the seawater, remineralization of phosphorus can explain what we see in the Mediterranean. So those are my take-home messages, and I will probably focus only on sources that we need to investigate to better reconcile observations with model, and those are combustion sources of iron and phosphorus, the dust emissions and how those are solubilized, and also the bioaerosol contribution to organic phosphorus that still remains an open question, its budget. So we found that the nitrogen to phosphorus anomalous ratio can be explained by atmospheric deposition. Bacteria play a significant role, and I will leave with those three questions. How the changes in the quality of nitrogen, that we have more oxidized now than less oxidized now and more reduced than in the past, for instance, and also the relative inputs of nitrogen and iron and phosphorus to deposition that change with the atmospheric acidity changes will affect the ecosystem functioning and the biodiversity. And what about the future dust? Here we assumed that the dust emissions remain the same, which is not true. And we know that there are significant variability in dust, and there's a lot of uncertainty on where dust emissions will go in the future. They'll go higher, they'll go lower. And finally, a question: how can we increase accuracy? can we use satellite observation, for instance, to constrain better the emissions and the deposition? And with that, I would like to thank you for your attention.
Thank you, Professor Karagirou, for this very interesting and insightful talk. We have, I guess, time for a question. I see a question from Jean. He's asking how regional climate change may change these nutrient fluxes.
Okay, I think this is quite a lot related to this dust, future dust, how future dust will change in the area. Probably we will have some there are discussion. We might have some intense, more intense events, and it might be that the geographical distribution of dust deposition will be different. And the other thing is also that we have higher temperatures, so chemistry will change also. And that means we expect that this acidity and also the oxidation, the oxidants will change into the environment. So the solubilization rate will change. So those all are things that we need to focus on them and understand them with regional chemistry climate models, I think.
Okay, so we have two more questions, and I think then we have to wrap up from Estadios Boutsoukides. So what is the seasonality of these fluxes and how important it is in the annual averages presented? So what is the uncertainty around?
For seasonality, I had some here. Those are the measurements showing the seasonality. So you see the position of ammonia is lower during summer because we have less rainfall. And the dissolved, the phosphorus and iron deposition will reflect also the deposition. I have the measurements here. Will reflect also the deposition of dust. So we will have a spring and autumn maxima where the nitrogen will have a summer maxima. And this is interesting because summertime we have a stratification of the seawater due to the warmer period. So it's when we expect that the atmospheric deposition will have most of the impact.
Okay, so we have another question about perhaps should we consider more measurements targeted at the solubility? And Professor Lervil is asking, is the soluble fraction of particular iron a linear function of the acidity, or is there a difference between crustal and combustion-derived iron?
There is I don't know how good the measurements are, but there is a consensus that the combustion-derived iron is more soluble than the crustal iron. So indeed, there is. It's not a linear function of acidity. So you need to understand from where it comes and which forms are there. And to the other question that was if we need more measurements of solubility, I think targeted measurements of solubility on the different components, targeting the sources of iron and not only in general, iron in general. That means looking at the combustion sources and the dust sources would be useful, beneficial. In particular for phosphorus, I would say, also. Yeah.
Thank you. So I think our time is up. Again, thank you for this very interesting presentation and the discussion. I guess we can continue the discussion also offline. So now we can move to the next contribution. It's an invited talk by Christos Fondoukis, who's affiliated with the Qatari Environment and Energy Research Institute, and it's titled Air Quality Modeling and Forecasting in the Arabian Peninsula, Research and Applications. So Christos.
Hello, hello everyone. Can you see my screen?
Yes, we can see your screen, but not your slides.
Indeed, I confirmed, Dr. Fondoukis. We can see you. Now we can see also your slides. We do see also your follow-up slide. Please check it.
Let me swap. Okay.
Before Dr. Fondoukis begins, I'd like to remind all to use the Q&A instead of the panel on your right-hand side. to facilitate the organizers and the chairs to follow questions. Dr.
Thank you.
The floor is yours.
Yes, thank you. Thank you for the invitation to present my work. I hope this will be of interest to some of the audience. So today I will talk about, let's see, okay, some research applications of our air quality modeling and forecasting work. And I will briefly spend a few slides on each one of these different applications. So we have looked at the historical frequency of dust storms in the region, the source regions and the relevant wind patterns. We get about, here in Qatar, we get about 10 to 20 strong dust storms every year and several more small-scale locally induced dust events. The predominant winds are the so-called shamal winds that bring dust in the country and are present mostly during spring and summer, but also during winter sometimes. The picture on the left here shows the main desert areas where this dust gets picked up from through the dust erosion process, the wind erosion process. Now Doha, which is in the east coast of Qatar and hosts more than 90% of the country's population, is a fast-growing city in an urban coastal desert environment. So on top of the dust, of the regional dust, we also have all kinds of pollution, right? We have strong traffic emissions, strong diurnal profiles. We have sea breeze circulation and sea salt particles. We have the desert dust particles, intense photochemistry throughout the year, strong solar radiation fluxes, nighttime nitrate chemistry. We have everything. So in terms of how interesting it is to do research in this, atmospheric research in this place is really very interesting, but also very challenging, especially for the forecasting applications. So basically the figure panels here show annual average spatial distribution of dust AOD over the Arabian Peninsula. We have published all this work. I'm going to skip this and go straight to our WRF-Chem work, but what I wanted to show here is that from these figures, you can easily see that the majority of dust is over the eastern part of the Arabian Peninsula. And this is due to topography and the predominant wind patterns throughout the year, which are mostly from the north and northwest. The model we have been using is WRF-Chem. It's an ideal choice, I think, for this region because it offers a variety of different parameterizations that could be used and combined in order to get the best predictions. It's such a complicated atmospheric environment, right? So many processes are happening at the same time, and not all different schemes work the same. We have gone through this exercise and we have tested different parameterizations. This is important in this region because it's particularly understudied and quite different from the mid latitudes of the eastern US, for example, for which this model was originally built for, right? So this is our forecasting configuration here. We are using a certain combination of gas phase and aerosol phase schemes that seem to work the best, but we have also run different aerosol schemes for different applications. For the dust forecasting, we use the Air Force Weather Agency parameterization with some important modifications that we have made to better capture the intensity of a dust storm and the spatial distribution. So to make the long story short, it's easy one thing to say, okay, the forecast of tomorrow shows a dust storm in a certain country in the Middle East, and a much more difficult task and more challenging task to be able to forecast the actual time the dust storm will hit a certain population center. For example, should schools which operate during daytime, of course, be alerted? And also the intensity, meaning how much of PM10 are we talking about? For example, should the aviation authority be alerted or not? And the time which the storm will die out. and people can safely go outdoors. So this particular parameterization seems to work with certain modifications that we have published to work the best for the region. This is just an example of a strong dust storm. We've been running this dust forecasting operationally for the last 3 years. It was a strong dust storm in January 2019. The animation on the left shows the hour-by-hour PM10 forecast. We produced forecasts for 3 days, and you can see the movement of the dust plume, which in this particular event originated from Iraq and Syria. The figure on the right shows PM10 predictions in blue color against our measurement data in red color at a specific location, the American School of Doha, which is downtown Doha, in which location we have one of our permanent continuously operating air quality monitoring stations. So this was a particularly successful forecast. Not everything is like that, every forecast. Both the model, every dust storm event, both the model and the data agree on a peak of about 5,000 micrograms per cubic meter. And over the whole day, the agreement is encouraging for the model. And this kind of model application is actually something that the local schools are very interested in here, to be able to use monitoring data together with the forecast to make decisions about, for example, when to allow children to go outdoors or stay indoors, etc. We've been working on the emissions continuously, I would say. Now, regarding anthropogenic pollution, we made a significant change in the emissions. We used the EDGAR numbers per country over the MENA region, which I think are representative numbers that are accurate for the whole region, but we reallocate these using high resolution land use information because really the EDGAR is doing a poor job in some of the countries here in a special allocation of emissions for WRF-Chem. The improvement is significant, and basically if we can capture the dust storms well and the urban pollution, then we should move into developing early warning systems. We are using some indices for better communication with the public of our air quality and solar radiation forecast products. So the goal is to have all these different indices publicly available through our web page well in advance of the big tournament next year, the FIFA World Cup here in Qatar. And basically we're using an air quality, so far, air quality health index, a dust storm index, a UV index, and a heat stress index. This is the air quality health index animation. Basically, it is based on the Canadian model, slightly modified. It's an hourly index instead of a 3-hour average, and calculated from hourly concentrations of ozone, NO2, and PM2.5. And of course, there are the different health-related messages based on the different index value. So in Doha, overall, most of the time, we are in the moderate or high index range. AQI is based on PM2.5 from the aerosol side. So we are using the dust storm index as well, together with AQHI, to capture all the aerosol activity here. And of course, the dust storm index is basically an AQI for PM10, not any different than the well-known AQI from EPA. So basically, there are 4 different colors for dust storms. And the yellow is the in-between case, which is the most challenging one, and the one that we pretty often have here in Doha. So basically, blue is relatively clean conditions. Red and maroon, we're talking about a regional dust storm, but the yellow is the in-between case, which it's a bit dusty, and it's mainly local dust, and is very often the case, much more often than the regional large-scale events of dust storms. The UV index is also a very interesting parameter for this region. There is a vitamin D deficiency in the population despite the intense solar radiation that we are receiving here all year long. And this has many reasons. We developed a parameterization for the UVI forecast of the desert climate, which has been published, and it is based on long-term measurements of broad body radiances under the influence of desert dust here. And the heat stress index also very relevant to the conditions in our area. In July, I can tell you that the heat stress index can reach 60 degrees Celsius here. So I think that says a lot about the need for such a forecast product. Now I'm going to talk about the different application, and actually one of my favorite projects, which mainly deals with the solar energy production of photovoltaics. How the high particulate matter levels that we have here in combination with high humidity affect the performance of photovoltaics and the solar energy production. We have a PV.
5 minutes, please. 5 minutes.
Okay. Thank you. We have a PV plant, a photovoltaics plant in the middle of the desert here. So this is very applicable and also for other PV or CSP plants in the greater region. Although there is a high yearly irradiance in this part of the world, as you can see in our solar atlas on the right map here, which was constructed based on long-term measurements of solar radiation, there are some aspects of the atmospheric conditions that pose challenges in the production of solar energy, right? For example, high dust concentrations, high humidity levels result in high soiling rate and deteriorating the PV performance by about 20 to 40% if we do no cleaning of the solar panels for 1 or 2 months. So we also have elevated temperature throughout most of the year, 32 degrees. And this is not good for the solar panels and the rich UV radiation spectrum. So using data from our outdoor solar test facility, we wanted to see if there is any correlation between ambient PM and PV performance, right? Solar energy production. And it turns out there isn't. Because high ambient PM doesn't necessarily mean that we will have a high soiling rate on the panels. A critical factor is the relative humidity. Only a fraction of ambient PM will deposit onto the panels, which also depends on the humidity at the time. Okay, so we assume that this fraction follows a behavior that resembles a step function, and we estimated this fraction and the resulting deposited cemented aerosol mass onto the panels. We found that above a critical humidity, 60 to 70%, there is an exponential dust deposition and cementation onto the panels. So very strong correlation between the energy output yield and this combination of cumulative PM and RH. And then we just extrapolated that all over our domain, and to calculate PV performance reduction due to soiling after 1 month with cleaning without cleaning all over Qatar. So that helps to develop soiling atlas for Qatar, and helps in identifying which locations receive the least soiling, decide where to put the PV panels, and for a specific PV plant, it helps in constructing a cleaning frequency for the solar panels and optimize the cleaning schedules. So you can estimate that for a PV plant of several gigawatts, it goes without saying that optimizing the cleaning schedule or forecasting the soiling is very important from an economic perspective. So I don't think I have much time left. This is the last
2 minutes
application.
actually, Dr. Foundoukis.
Okay.
2 minutes.
So I will skip through this last application quicker. Basically, we use the same model for a quite different application, dispersion of radioactive material from hypothetical nuclear accidents in the region. We use WRF-Chem with passive tracers to develop tools to support national authorities in their emergency preparedness and response plans in case of nuclear accidents. We have some nuclear power plants in the region. I will skip the methodology. This shows the hourly effective dose of iodine to the public from inhalation for December, just an example, 1 month. This is multi-year simulations to capture the different meteorological patterns. And we have one power plant, a nuclear power plant, very close to Qatar in UAE, and another in Iran. And this is how the dispersion will evolve. So I will, and these are some of the maps that we develop for every month for, monthly maps from multi-year simulations. I will stop here and just leave this final slide up for during the questions. This is what I think, you know, the way forward looks like for research and applications in the region, in the Middle East. Thank you.
Thank you, Christos, for this presentation. It's nice to see all the different ways you're adapting and using your model for applications. So we have a few questions. Please, from the organizers, I have a request. Can you use there's a specific question component in the chat box and not the actual chat box to ask questions. So I will start with the 3 questions I think are somewhat related. So using these several years of operational dust event forecasting, first of all, which dust episodes from which source regions are the most difficult to simulate? And could you analyze causes leading to poor predictions? And finally, do you see any trends in the dust amounts in the recent years?
Thank you. So the most difficult to predict are, I would say, some local dust events or near local, which we usually call them here haboobs, and they are triggered by thunderstorms sometimes. And yeah, this is these are very quick and very sudden dust storms that sometimes we fail to forecast. In terms of trends, it's not easy to say. Overall, we don't see any specific, notable increase or decrease in dust storms. I would say they are more or less the same over the years. We see, for example, most of the dust storms arrive here in Qatar between January and April, and that is pretty consistent over the past 10, 15 years. And the main source regions, as I showed earlier, are from the Saudi Arabia, deserts in Saudi Arabia, in Iraq, in Syria, etc.
Okay, and another question about the Earth Quality Health Index. Do you include sea salt in that?
No, the Air Quality Health Index is based on this Canadian model, which includes NO2, ozone, and PM2.5. But you know, we plan to use AQIs for each pollutant separately. This is just, let's say, an overall AQHI that we started with.
So when you had this large plume coming from the Arabian Sea, that was recirculated dust, I guess?
Right, yes, yes.
Okay. And then there's another question, I'm not sure I understand, but I will just try to read it. So the location of the station, coast, middle of the country, next to Saudi Arabia, how many stations and data collected from the field for correlations since when? That's the question.
So the correlation I showed was for the solar energy project was from one station only now, which was right next to our solar panels in our outdoor test facility. Overall, air quality stations, we have 6 spread across the city, 6 continuously operated monitoring stations, and they have been operating some of them since 2012, some others are more recent, so we have at least 2 or 3 years long measurements.
Very well. Thank you, Christos. I don't think there's anything else. So to keep on schedule, I think we should move on to the next talk. So I would like to thank our 2 invited speakers for their excellent contributions. And next is George Georgiou from the Cyprus Institute. He's going to be giving a talk on real-time air quality forecasting over the East Mediterranean, again, using the WRF-Chem model. So George, if you could get your slides full screen, please. And then just a second.
Can you see my screen now?
Yeah, we can see your screen. You can see the PowerPoint application, but okay, now we can see your slides. So please go ahead.
Okay, so good morning, everyone. So my name is George Georgiou. I'm a postdoctoral fellow at the Environmental Predictions Department of the Climate and Atmosphere Research Center, and I'm going to talk about real-time air quality forecast over the Eastern Mediterranean with WRF-Chem. So at the Cyprus Institute, we perform daily 3-day ahead air quality forecasts. In order to do that, we're using the WRF-Chem model, which is the weather research and forecast model covered online with chemistry. On the top right, you can see our model domain. We are using 3 one-way nested domains in order to go down to 2 kilometers horizontal resolution over Cyprus. We also use an extended outermost domain in order to include the major dust sources in the region and minimize the impact of lateral boundary conditions. We are using lateral boundary and initial conditions from global models for meteorology and chemistry. And of course, emissions are included in our simulations. More specifically, anthropogenic emissions are provided as external output, and biogenic dust and sea salt emissions are calculated online throughout the simulations. For the island of Cyprus, we have implemented a high-resolution emission inventory from data provided by the Department of Labor Inspection of Cyprus on a horizontal resolution of 1 by 1 kilometer. And on the top right figure, you can see the comparison between the EDGAR emission inventory and the high resolution emission inventory in terms of the spatial distribution of emissions. We see that the new emission inventory resembles much more accurate anthropogenic activities. Apart from the spatial distribution of emissions, we also have markedly higher total CO and NOx emissions in the new emission inventory. On top of that, we also included monthly, daily, and hourly variation of emissions, and these emission factors were derived after the Lotos Euros documentation, and more specifically, the emission factors were calculated per species based on the primary emission activity in Cyprus. The implementation of the high-resolution emission inventory resulted in an improvement of up to 60% in the estimation of the concentration of atmospheric pollutants at the urban areas, and of course, more accurate representation of the diurnal profile of the atmospheric pollutants. So these are the average NO2 concentrations at the top, the forecasted concentrations for winter and summer, and the field circles indicate the corresponding observed concentrations. it is shown that we have higher NO2 mixing ratios during winter, and near the urban centers, the locations of the two power generation stations, which are located here, and the eastern part of the island, which is affected by emissions from within Cyprus. And this increased NO2 concentrations result in reduced ozone mixing ratios at the same locations. And we also see that the whole island population is exposed to ozone above 40 parts per billion during winter and above 55 parts per billion during summer. Now let's see how this compares to how our forecast compares to observed values and the CAMS model. CAMS is a state-of-the-art model. It's actually an ensemble of models which provide daily forecasts over Europe. With gray color, we can see the observed values, and with blue color, the forecasted values, mixing ratios from WRF, and with red color, the forecasted mixing ratios from CAMS. We can see that compared to CAMS, we have improved normal mean bias for WRF chem at the residential and traffic stations by up to 90% in NO2 and up to 31% in ozone. The industrial stations, though, we have an overestimation of NO2 by WRF chem, and this is something we are still investigating, and we are taking into account the fact that actual emissions at these locations are not emitted in the surface as it is considered by the model. So we are investigating that maybe in some cases actual emissions are emitted above the boundary layer, so we have this overestimation by the model.
2 minutes left, George.
Okay, so these are the diurnal profiles of NO2 at all of the stations operated by the Department of Labor Inspection. We can see that we have more accurate representation of the diurnal profile of NO2 by WRF chem, and even at some traffic stations like the Rolnaga traffic station and the Nicosia traffic station, and of course the residential station. So at these stations, the WRF chem is able to capture the morning and evening peaks, and these peaks in NO2 in NOx concentration actually result in decreases in ozone mixing ratios, which are only captured by the WRF chem model. Finally, these are the PM2.5 concentrations. We can see that during the summer we have similar behavior between CAMS by WRF chem and CAMS, and actually there is the performance of WRF chem compared to CAMS is they have equivalent performance. So to summarize, we have employed the WRF chem model to produce accurate air quality forecast over the Eastern Mediterranean. By improving the spatial and temporal resolution of the emissions, we see improvement of scale in the representation of the magnitude and the diurnal profile of atmospheric pollutants, and especially in the case of NO2, where we see an improvement of about 19%, and in the case of ozone, where the improvement is about 31% in the accuracy of the forecast. So thank you very much for your attention. If you have any questions, I will be glad to answer.
Thank you, George. Are there any questions from the audience? So there is a question. So it says, impressive work on the local emission inventories, and thank you for the talk. Do you have a comparison of WRF and CAMS for long-range transported species, such as example given dust? And do you have a verification of the vertical profiles?
We haven't looked at the vertical profiles yet, but this is something we could do. We could examine. Regarding the long-range transport species, not yet at this point. We don't have it, but we have the observations as well. For example, for CO, so we could also have a look at these species.
Thank you. Perhaps I can add, because I'm familiar with the work, that this is underway with collaboration with the National Observatory of Athens. So the vertical distribution of dust and PM10, as well as the dust optical depth, is now compared with satellite observations, as well as LiDAR data. And that will be published soon. I think there's a presentation on that in tomorrow by Vangelis Kyriakidis. Any other questions? If not, I would like to thank George for his presentation. And we can move on to the next talk by Sergei Osipov, who's affiliated with Max Planck Institute of Chemistry in Mainz. And he's going to be talking about modeling air quality in the Middle East during the 2017 Aqaba campaign.
Good morning, scholars. I'm glad to present our work today, modeling work today, and my talk will focus on the Middle East and the air quality in the region and the recent observational campaign there. Let me precondition this talk by saying that air quality in the Middle East has a very distinct type due to combination of natural and anthropogenic emissions. And as you know, dust received a lot of attention in the recent research due to the integral role that it's playing. But we also know that anthropogenic influence in the region is profound, and it's evident simply because of the region's share to the global emissions. For example, Middle East contributes more than 10% of the global CO2 emissions. And today I would like to target the following discord. Dust is usually conventionally assumed to dominate air quality, while the role of the human-induced trace gases and aerosols remain largely uncertain. And I think this is because of the lack of the observational constraints, which is a significant modeling challenge. Exactly to fill this gap, in 2017, there was a ship campaign around the Arabian Peninsula, which studied the atmospheric chemistry for a couple of months. And today I'm going to use the WRF-Chem simulations and these observations to give a very brief overview of the air quality in the region. From the previous, I'd like to start with ozone chemistry. And from the previous research, we already know a few things that we have to represent in the model to get it right. Namely, the strat-trop exchange plays an important role, and in summer it contributes up to 25% of the atmospheric column. There is a long-range transport of air pollutants from the Mediterranean, and recently published work shows that the ozone production in the region is mostly NOx limited, meaning that reduction of NOx emissions is a viable strategy to control the ozone levels. This is the comparison of the observed and simulated ozone during the campaign. And you can see that several regions, namely Gulf of Suez, Northern Red Sea, and Arabian Gulf, stand out as the exporters of the ozone. During the campaign, ship was stationary at Jeddah and Kuwait for several days, and this is where we see the ozone titration taking event when the NO and ozone is converted to NO2 during the nighttime. And what I also like to highlight is the missing formaldehyde source over the Arabian Gulf, and we can pinpoint it to the flaring. First of all, because of the peroxy radicals exhibit similar variability over the Arabian Gulf, and we know that photolysis of formaldehyde is a source of peroxy radicals. And then using the backward trajectories and the lifetime of formaldehyde, we can say that it's flaring. This is the long-term. This is the mean fields that we use to quantify the health effects, and you can see for the ozone, the entire domain exceeds the recommended thresholds. For the NO2, the special concentrations are more patchy, but still the most populated areas are covered. Let me change gears and talk briefly about the aerosols. The overall concept is the following. The unspeciated size distribution was measured during the campaign, and within the PM1, the AMS and accelerometer speciated the sulfate, ammonium, organics, nitrate, and black carbon. Ideally, we would like these two curves to coincide, and that would mean that we know the composition of the aerosols. But if there is a gap, it's probably due to additional aerosol types. And in this case, we can use another instrument, ion chromatography, to deduce if it's dust, sea salt, or water. And for larger particles, there is a particle loss taking place at the inlet, and we have to take this into account. This is what PM1 looks in observations. And as you can see, the black line shows the unspeciated concentrations, and which sits nicely on top of the speciated components, for example, in the remote atmosphere over the Arabian Sea, Southern Red Sea, Northern Red Sea. But there was a couple of events when things didn't agree. For example, over the Gulf of Suez, there was clogging of the instrument taking place due to homogeneous nucleation of the organics, so we can explain that. And over the Arabian Gulf, if you look at the difference of the dry and wet PM1, water fills the gap. And so from this slide, we can conclude that PM1 is most anthropogenic. There is no dust in here, and 4 azole types constituted. And the ternary solution of water, ammonium, and sulfate over the Arabian Gulf is stands out. I will go through each type of the aerosols quickly to show the model skill in simulating those. And to get the organic aerosols right, it's critical to use the aging mechanism, which is volatility basis sets in our case. And the relatively good comparison across different regimes of pollution tells us that VOC sources are well known and that the model performs well in terms of the turbulent mixing and the representing metrology. We diagnose that in rural areas, 100% of the organic aerosols are primary, but in the urban areas, for example, of the Suez and Arabian Sea, half of it is due to secondary organic aerosols production. Sulfide chemistry is relatively straightforward, and because this sulfuric acid is not very volatile.
2 minutes left.
Thank you. You have to get the point sources right. We know that over the Arabian Gulf, several sources were identified, but still there is additional sulfate has to be added due to faster oxidation of this SO2. With black carbon, you can get it right in 2 steps. If you only consider speciated black carbon emissions, you'll be underestimating the black carbon, but all of the inventories provide unspeciated PM2.5 as well as organic carbon with black carbon, and the residue is often ignored. If we take into account, this adds an additional teragram and removes the biases across the different regimes, but we're still missing black carbon of the Arabian Gulf, and we can quantify how much needs to be added. And at this point, it's clear that it's not just SO2 missing from flaring, but the flaring itself are not represented in the inventories, and all of these species has to be added, and not only formaldehyde, black carbon, and SO2, but others too. I'll skip the dust slide. I'll just briefly mention that we use unimodal size distribution, and putting anything into the coarse mode will provide inconsistent results with the optical properties. And it's critical that the tuning of the dust happens only after the anthropogenic aerosols were constrained. And why I say that it's inconsistent with optical properties is because we can simulate those pretty well, and we diagnose that half of the column optical depth is anthropogenic. In my previous work, I studied the world's largest radiative forcing over the Southern Red Sea, and now we know that half of it is dust and half of it is anthropogenic. This plot shows the angstrom exponent, which tells us that we not only simulate the concentrations right, but also the size distribution, spectral size distribution. Overall, we have confidence in the model skill representing the air quality, and we quantify the health effects. This table here shows the death rate in the Middle Eastern countries, and we quantify the excess mortality due to exposure to PM2.5 ozone, and we compare that with the COVID. As you can see, the excess mortality is in the order of 10%, which is comparable to the yearly mortality due to the ongoing pandemic here. And I would like to stop here and just highlight that the anthropogenic pollution and human-induced presence in Middle East is profound. And as you can see, it's not only air quality, but also it's now an important climate driver, and we have to account for that if you want to simulate the present and the future climate in the region. Thank you.
Thank you, Sergey, for this excellent presentation. Are there any questions from the audience? Sione, do you have a question? Or are you?
Just getting ready for my part.
Oh, okay. Are there any questions? So we have a question from Christos Foudouguis. So why is the mortality in Oman particularly high? I think it's referring to the to the table you showed with the
COVID-19.
Yes.
Well, yeah, I don't have a good answer for that. We can clearly see in outliers, for example, in Egypt and Yemen, which show low numbers for the mortality due to COVID, but I'm not sure on the other side of the spectrum that higher than, maybe it has to do with the population density.
So
the higher rates in the
to calculate those numbers, you extrapolated to a full year simulation based on your results from the campaign. Is that correct?
Yeah, so the air quality mortality is based on the mean fields, and this is based on the response functions, but the COVID data is coming from the Statista, so it's from provided.
Yeah, well, I understand. I'm thinking about the air quality data. So you
yes, so we what I was trying to show is that model has a skew in simulating the air pollution, and then we have a longer simulation. We average those fields and quantify the long-term exposure. So this is happening on a yearly basis. What will you see if you expose it to this on a yearly basis, long-term?
And then one last question: how realistic is it to consider only one modal distribution of aerosol optical depth?
Only one model distribution. What do you mean by one model distribution? Yes, for the dust. I think it's the most realistic because first of all, it's consistent with the theoretical distribution of the brittle fragmentation theory by Jasper Koch, and then the emitted size distribution is a parameterization, but usually is used in the modeling work. And like I said, putting anything in the accumulation mode produces PM1 concentrations which are too high. We don't see this in the observed size distribution. And then this is also optically active particles. So adding anything into accumulation mode produces incorrect AOD. So the overall feeling was that if you don't have the anthropogenic emissions, then you end up tuning dust and adding it into the accumulation mode, and you get the wrong result, semi-right result for the wrong reason. And the concentrations that we get from dust in PM1 and PM2.5 are coming from the left tail of the size distribution. And also I have more diagnostics which show we can constrain the dust deposition in various regions. That agrees very well. The dust deposition to the Red Sea that we has a good agreement with previous studies. So I don't see any other way of having not uniform model distribution.
Okay. And finally, could you evaluate PM1 simulation, or is there effort to simulate particle number concentrations?
I'm sorry, could you say it again?
Could you evaluate PM1, so particulate matter lower than 1 micron, or is there effort to simulate the number concentrations at this threshold?
The numbers that I showed, the unspeciated size distribution is discrete, so we can do PM1, PM 0.9, 0.8, and what I model is using MADE. This is can be analytically integrated. The reason I show here strictly PM1 is because the speciated part was in bulk done by aerosol mass spectrometer, and it's a convenient threshold.
Right. So thank you.
Dear Theodores, before we move on to Yoni, I would like to make a clarification. For those of you who are panelists, you can ask your question if you use the scroll down button in the chat section and send question to staff. Then it will go to the question section and it will be better.
Perhaps you can demonstrate this during the break. You can share your screen and do an example of this. Andre, I think will help everyone. So let's move to Yoni to keep track of time. So Yoni Kusta with the Cyprus Institute. It's going to be giving a talk on satellite-derived emission trends, uncertainties, and implications for atmospheric modeling. Yoni, please go ahead.
Yes. Do you see my screen and do you hear me?
Yes,
we confirm both. We see you and we see your screen and we can hear you.
Good, great. So this is work done in the framework of the MetaSat project with ESA, where we tried to use satellite information in order to update emission inventories. However, in this presentation, I will highlight some uncertainties and the implications for atmospheric modeling. So the motivation for our work was that, as we all know, emission inventories are a base component of air quality modeling, and are the factor that usually define, as also shown by a presentation from Dr. Georgiou, define model skill, model performance. Unfortunately, emission inventories, the official ones, are updated every 5 to 10 years, 5 being on the very optimistic part of updating frequency. And those emission inventories are based on reporting data or sometimes proxies or older emission inventories. However, in the Eastern Mediterranean and Middle East region, where abrupt changes happen either due to unexpected socioeconomic factors or geopolitical factors, this update frequency is not enough to capture changes that happen in this decade, in intermediate stages of the decade. And also in the EMA region, there are a lot of non-reporting countries where proxies are used to estimate emission inventories. New facilities start operating in this period, and the magnitude of emissions is usually understated. So the objective of this work was to utilize satellite information that is continuous in order to update the emission inventories and maybe be able to capture some abrupt changes caused by unexpected factors that are changes that usually are not in line with representative concentration pathways. The methodology of this work is based on previous work by Lamsal in 2011. However, their approach was at the early scale and global one. So the concept is that since a satellite can capture the vertical column density of NO2, which is the concentrations integrated over a column at a monthly scale, how can we use this information to see what changes with emission? As you all understand, the ratio of emissions to vertical column density is not 1 to 1. I'm sorry. So models are used to try to linearize the non-linear nature of the relationship between concentrations and emissions by producing a factor that brings the ratio of the emission changes to the ratio of the VCD changes. This factor is called beta. And when we have this beta, this behavior of concentrations versus emissions per each grid cell, then we can upscale the emissions of year X, in our case, the emissions of year 2010, to any year of interest, in our case 2015, by using the observed VCDs of 2010 and 2015 and this beta factor. So as you understand, we need a model, and this is the weather research and forecasting model coupled with chemistry. We need emission inventories, and these were the 2010 Edgar HTAP version 2 emission inventory, and we need vertical column density from satellites, which we got from the Quality Assurance for Essential Climate Variables project, which is a community algorithm that brings together all algorithms used by different research groups in order to produce tropospheric, stratospheric, and total NO2 column densities. From 1996 that GOM was available until 2018, where we have the OMI, the OMI satellite observations. So we applied the methodology at regional scale, and later on I will show some results from the global scale. And our main difference with previous work was that we repeated the whole procedure for every month of the year. And as we saw, this is very important because the behavior of the chemistry is not similar in winter and summer months. In these plots, I show the beta for all months of the year 2015 from January to December, and it's quite clear that if we average this behavior into annual means, that we will miss some important information, especially for the summer months where photochemistry is more intense. And we will smooth out the effect of beta, so we will smooth out the expression of the concentrations versus emissions behavior, at least in our region. So as we see clearly here, summertime spatial variation is more pronounced, and it shows more clearly the chemistry paths and the VOC availability during summer months. And in winter, this is more smooth out, so it's more linear, the behavior of emissions versus concentrations. And in order to assess some uncertainties in this methodology, we also used OMI and GOM2 satellite data that have different overpass time, but we saw that the uncertainties due to the selection of the satellite were not so important. What is really important is this reduction rate that we use in the model sensitivity test to produce beta. We can use 30% and 50%. We used these two ratios, and we saw that summertime uncertainties of the beta factor are lower, owing to the really fast reaction rates and very intense photochemistry during summer months that lead to reduced lifetime of NO2 in the atmosphere in summer. So it's very important for complex chemistry region like EME region to be able to assess properly what is the right reduction rate in which the linearization is more close to reality. However, from now on, the results that I show are for the 30% beta selection. And in this case, after having beta, we updated the 2010 EDGAR HTAP monthly emissions into 2050 monthly emissions based on what the satellite saw as a change between 2010 and 2015. And after updating the emissions to 2015, we reproduced the simulation for this year to see what is the impact on concentrations of NOx and ozone in our area of interest. So overall, we noticed that there are areas with pronounced differences, and those include areas in the EME region where population movements occurred. So we have some hotspots in 2015 that were not there in 2010, such as North Africa, Lebanon, due to refugee camps, expansion, etc. We saw differences in regions with high industrial activities, an increase in emissions of NOx and therefore in concentrations of NOx in this area, such as Israel, Coast and Gulf region. A slighter but still evident increase over Benelux countries and also Germany, northern part of Italy, and several locations in Eastern Europe like Poland that might be associated with increases in primary emissions due to transport or coal power plants and other industrial facilities. And in the EME regions, there were the two very evident conglomerates, Athens and Istanbul, that exhibit noticeable differences between 2010 and 2015 emissions. After the regional application to be compatible with the previous work, but as I said, in monthly frequency, while the first application was at yearly averages, we repeated the whole process at global scale with the use of the ECHA model. And as you can see on the left plot, where I show a couple of selected months, April and October specifically, you see that there even can be opposite trends in emissions for specific months. And these trends are smoothed out in the annual differences that you can see on the right top plot. So in April, for example, overall, you see a reduction in emissions between 2015 and 2010, and the differences shown here are updated by minus base emissions, while in October, there is an opposite trend. There is an increase in VCD, which brought an increase in emission fluxes between 2010 and 2015. But overall, at an annual scale, we noticed that the trends from 2010 to 2015 are overall positive for Europe and North Africa. So there is an enhancement of emissions in 2015 compared to 2010. While over India, we see a general reduction of emission fluxes in 2015 compared to 2010. Now, there is yes, 2 minutes.
Please wrap up because your time has ended.
Okay. Oh, I didn't hear the 2 minutes Anyway, this is the last slide. Over Asia, there are two distinct zones with opposite emission trend signs. There is the northeast one and the southwest area, with the southwest region following the negative trend pattern over the Indian region. So this is my presentation. I could say that there is a lot of potential for satellite data to be used to update emission inventories. But we should pay specific attention to areas with complex chemistry like the EMA region. Thank you.
Thank you, Ioni. We have a question. Will you use this method to update to even more recent years?
Yes, thank you for the question. As long as there are available satellite data, we can do this. And in fact, we have done this up to 2018, which is the last year with available OMI data from the project that I mentioned, the Quality Assurance for Essential Climate Variables. As they go on, of course, since the trend beta factors are ready, then we can scale this up to any year of available satellite data.
Right. So, and then we have a comment and question. So, the inherent lack of knowledge of what would happen if the complex system of the cosmic climate and atmosphere were to be manipulated is one reason for the caution policy that should be adopted. So, what is your assessment of geoengineering at the level of atmospheric modeling? Do you think that before embarking on the use of geoengineering, the following question arises: are we sufficiently sure that the natural balance of the climate and the Earth will continue after the use of geoengineering?
Well, the question is not really clear to me. Maybe I can read it on the chat. No, I can't.
I think the question, I don't know how it relates to the talk, but I think the question is, given this complex balance, the complex balances in the Earth system, and do you think that geoengineering would be a good idea in general?
Well, when there are no other ways, even any methodology, even if they have uncertainties, should be utilized. So better than nothing, you can use something.
Okay.
With all the uncertainties and problems. Thank you.
Other questions? If there are no other questions, I would like to thank Ioni and all the other speakers of this session. I think we are right on time. However, there is a break scheduled at 11, so there is still some time. I don't know if
Theodoros, sorry to interrupt you. If it's okay, before going on a break, I would like to show you, especially for the panelists, how you can submit your questions, because the panelists cannot see the question section. So,
yes, of course. Whoever wants to follow through this demonstration. Okay, before we go to the demonstration, there's a question for Ioni. Are these inventories available, I guess, to be used by others?
Yes, we can discuss further. The trend factors are available, so you can apply them even to your own emission inventories, but also on OMI, based on OMI data, these inventories are available up to the NOx emission inventories. Okay, I should clarify this. This is not for all species. It's for the scaling of NOx emissions from 2010 to 2018. If you have further questions or specific needs, of course, contact me and we can discuss how to use this data.
Okay, and which other species could you address?
With this methodology, only NOx, because it's a fast track chemistry species, and you do not have an outflow of NOx from one grid cell to the other, which complicates things with other species that are more long-lived. However, I am aware of other groups which work with SO2 species, sulfur dioxide upgrading from satellite data, and I can provide you this information also.
Okay, and this can of course be used in numerical models. Yes.
Yes, you upgrade the same format as Edgar HTAP original data set is. You can just apply these trends per grid cell of the emission inventory, and you have scaled emissions. It's the same thing, and then you use the same processor to produce for numerical models.
Okay, so thank
You're
you.
welcome.
And thank you, everyone. So proceed now.
I will make the demo. Can you see my screen, Theodore?
Yes.
Okay. You see the chat section now?
No.
You don't see it?
You have to be not in full screen for everyone to see your chat section. So.
You see it now?
No. I think you have to see your whole desktop if it's possible.
That's what I chose. My
Is
screen.
there a way for your slides not to be full screen or?
Let me. Now you see the chat.
No, but what I would propose, perhaps we can just take a couple of screenshots and then before the next session or during the break, you can show them as a presentation or have them during the break, have them on the, do you think that's possible?
I think so, yes. We will try that.
That would help everyone, and then everyone can take a break, and whenever they're back, they can see the way to do this.
Okay, I will be jumping back in. So thank you, Professor Christoudias, for chairing the session on atmospheric modeling and prediction. Now, it would be great if we could start earlier, but because there are people who might be joining exactly at the predetermined time to observe the air pollution and impacts session, let us have a longer break. So I would like to invite everyone back at 11:10 Cyprus time, as per the program, as exactly per the program. And then during that time, I will invite Professor Nikos Michalopoulos to be the chair and to chair the air pollution and impacts session at 11:10 Cyprus time. In the meantime, we will try to prepare exactly a couple of screenshots and to write to all the way to send questions, which shouldn't be too technically challenging. So 11:10 Cyprus time for the air pollution and impacts session chaired by Professor Nikos Michalopoulos. Have a nice coffee break all. See you in about 20 minutes. Thank you. Dear colleagues, we will start again in 2 minutes. 2 minutes, please. All right then, dear colleagues, again, good morning, good afternoon, and good evening, depending on your time zone. Just reminding a few technicalities again. Each session has a chair. For this session, we have Professor Nikos Michalopoulos. The chairs are responsible for calling the sequence of colleagues, of speakers. There are two types of deliveries. It's invited speakers and oral presentations. For invited speakers, we have a duration of 15 minutes, 1-5, followed by 5 minutes Q&A. And then for oral presentations, we have a duration of 7 minutes, followed by a 3-minute Q&A. We do have timekeepers, so please be ready to accept very short interruptions at 5 minutes and at 2 minutes as reminders of time left for the invited speakers, and then for oral presentations, just one reminder at 2 minutes, and then you will be invited by the chair to wrap up. As per the questions, I am orally giving you a description now, but I will also send to all organizers and presenters. If you look at your right-hand side panel, you will see 2. And then if you go to the downwards arrow prompting you to specify who to send the message to, if you scroll down all the way down, there is a send question to staff option. Choose that and write your question. Alternatively, if you cannot find that and you can find the name of the chair, send it to the chair. But the right way to do it is to choose send question to staff from the 2 options that you anyway have. So without further ado, I would like to invite to the virtual podium Professor Nikos Michalopoulos to chair the session on air pollution and impacts. Professor Michalopoulos, please, the virtual chair is yours.
Thank you, Pierre for the introduction and for all these nice tips for the presenters. We will start with two invited speakers. The first is Dr. François Dulac from CEA LSE France, and he will talk about Charmex, a quick look at the chemistry aerosol Mediterranean experiment, Charmex legacy. François, the floor is yours. You have 15 minutes.
Okay, can you see me? Good.
Yes.
I'm trying to share my screen. Do you get it?
No, just we can see you. Yes.
Okay.
Yes.
Good.
Yes,
So
You see your screen, but not the presentation. So if you can put it at full mode.
it is on my screen, but maybe it's a matter of double screen here. Let me check if I remove this. Is it okay now?
No, I don't see any change. Oh, now it's better. Okay, yes.
You get it. Good.
Yeah.
Okay, I've lost it on my screen. So thanks for invitation. I'd like to talk about the CHARMEX experiment, which stands for the Chemistry Aerosol Mediterranean Experiment. This is a program which was initiated long time ago in 2007, and which has been supported by a French program called MISTRALS, which stands for Mediterranean Integrated Studies at local and regional scales. And the question was to explore the Mediterranean region on a multidisciplinary way, and in particular ask a question about its future inhabitability. And this program was later endorsed by the Parliament Union for the Mediterranean, and it has federated national efforts from many countries. Our overall objective was to make an updated assessment of the atmospheric pollution and of its impact in the Mediterranean region, and of course, look at their evolution in the next decades. So the overall strategy was, as for all big projects in atmospheric chemistry now, was to integrate multi-scale observations and modeling and satellite surveys. But the project has had a very large observational component with several large regional campaigns, in particular in the Western Basin. But we have also included more local field studies in various specific environments. We also set up several stations and several years of monitoring, especially of dust deposition. Of course, we have developed large-scale remote sensing analysis and extensive modeling. There has been more than 20 French labs and several tens of foreign labs, which finally contributed to this effort. So there is a large list of papers produced in this decade of research. You can find most of them in a special issue in ACP and AMT. And the full list of publications and related PhDs is available on a web list, on a web link that I've given here. There's also a database where most of the data produced during these experiments is available. So I will basically show here only a few of the results which I consider the most important. And I will make some advertisement for a review book on atmospheric chemistry in the Mediterranean, which we have produced and which is now in press by Springer. So to start with, I have this window which bothers me here. Okay, sorry. To start with, there has been 5 regional campaigns with large airborne means. I will illustrate some of them here. Many other campaigns, especially we have been working in Mediterranean forests and in large cities. We have also reinforced the Aeronet network in the region by putting several new instruments, especially again in the Western Basin, but not only. Also in Northern Africa. And we have had this weekly dust deposition monitoring network, which has been operated for several years. I will illustrate here only a few of these, a few experiments of these huge observational efforts, and I refer you to the introduction chapter of the book in press to have more details on all what we have been doing in this decade. So the top left panel shows several transects that we have been performing through the Mediterranean, basically from France to Greece or Cyprus. Two of those plotted here were ship cruises. One was basically a small sail ship with aerosol optical thickness observation of the maritime Aeronet network. Another one was a large vessel with a campaign in which we have addressed both atmospheric observation and oceanographic observations. And in particular, we have been targeting rainfall deposition, and we were able to sample 2 rain events in the Ionian Sea and south of the Balearic Islands, where we could check the impact of this deposition on the oceanographic biogeochemistry. And the last one was a transect with the French Falcon, again from France to Cyprus, where we could measure a number of gas species and aerosol in the mid and upper troposphere, and during which we could observe 2 events of a very long range transport of biomass burning from North America or desert dust from the Sahara, which came back over the Mediterranean after a long way over the Atlantic. The top left panel is a network of background stations, which we have been operating for background aerosol measurements. You can see the different periods and the different species that were measured here. Again, mainly in the western part, but not only. The bottom left panel is an example of one of these large campaigns, which we called the SOP for Special Observation Period. In summer 2013, there were 2 aircraft operated from Sardinia, which flights are plotted here. There was CNES drifting balloons launched in the lower troposphere with ozone or aerosol instruments, and there were about 20 of these balloons which could offer Lagrangian type measurements of ozone or aerosol size distributions. We had also an ultralight in Malta making nice measurements, for instance, of ultrafine particles. And we also set up a network of background stations in various places in Spain, in Balearic Islands, in Lampedusa, south of Sicily, and also 3 different stations at different altitudes in the north of Corsica. And the last one is, here highlights our efforts of campaigns in large cities of the Eastern Mediterranean, and I will illustrate some of the results we obtain on VOCs. The VOCs are, important because they are precursors of major secondary particles, and also they are part of the ozone chemistry. So we've been measuring a number of these species in various cities in the Eastern Mediterranean, and we compare here the data on the left plot obtained in Marseille, Athens, in Istanbul, and Beirut, and we can see that there is a clear increase in concentrations going from the western cities to the most eastern cities in the basin. An important results which we obtain and which has been already stated by previous presentation is the great difference between large-scale emission inventories and local emission inventories. And based on these VOC concentrations, we were able by 2 different methods, in fact, to compare with emissions inventories. And we can see that even local emission inventories plotted here for Beirut and Lebanon look underestimated when we compare to the concentration of VOCs we obtain. And if we refer to the global inventories here, which is plotted in red, there is almost a factor 10 underestimations for Lebanon in terms of VOC emissions. So again, it looks very important to go to fine scale of these species emission inventories for air quality modeling. The next thing I will illustrate here is those drifting balloons. We have been performing 3 campaigns, launching balloons from about 300 meters in altitude up to more than 3 kilometers, measuring either ozone with a modified electrochemical sound, so that we could measure ozone for over 1 day and not only a few hours as in the balloon soundings. And we have also developed a new optical particle counter, which was very sensitive thanks to measurements in the near forward scattering direction, where you have a much more important signal. So in terms of
5 minutes.
Okay. For ozone, we can see here a comparison between observation and the forecast by the MAC model, and we can see clearly that the increase at the sunrise was much more pronounced in the observation than with the model. Unfortunately, we have not explored more what was the reason for this underestimation, but this data set is available for making more detailed comparison of these daily cycle of ozone. We observed even in the lower troposphere some net increase rate in ozone, which are very original data. In terms of aerosols, we have been flying from Menorca mainly in dust plumes, and from all these observations, which are the points here, we could fit the size distribution up to more than 30 microns. And in all cases, we observed that there was a mode at more than 30 microns, which remain constant during the whole transport over 10 or even more hours, when we know that the theoretical settling gravity velocity of these large particles is several kilometers per hour. So they are not supposed to be transported there. And most of the models, they consider only particles up to 20 microns in the emission scheme, because these large particles are not supposed to be transported. And they are making here about 15% of the total mass, so it's not quite negligible. Another important result is that we were able to perform a first hindcast aerosol modeling exercise with assimilations of measurements from a LiDAR network that is plotted here on the Google map. This is basically the EarlyNet network with 1 or 2 more LiDARs from Charmex. And we compared the simulations assimilating the aerosol data from 1 to 3.5 kilometers in the column. And we could check that assimilating those data was improving the surface PM forecast up to about 1.5 day forward. And of course, we improve the AOD, which is the aerosol column content, but we also improve with these data from altitude observation the PM surface concentrations.
2
finally,
minutes, please, Dr. Dulac. 2 minutes.
Okay. Finally, a last result is the aerosol climate interaction that we've been able to model with the regional coupled models, where the sea surface temperature has some feedback from the solar radiation, and in particular, you know that the aerosol decrease the surface solar radiation by numbers which are averages on the middle plot here on the yearly time scales, and we can see numbers more than 20 watt per square meter decrease in surface solar radiation. And this results in a decrease in average precipitation over the basin by something like 0.1 to 0.2 millimeter per day on average at the yearly time scale. So this is more than 10 up to 15% of precipitation reduction due to the radiative effects of aerosols. So finally, to conclude, I'd like to advertise this this new book that is now in press. You will find here an overall review of the atmospheric chemistry in the Mediterranean. We've been considering the 4 and even 5 decades of research in the region to wrap up the main results, and also we issued some recommendations for future research. So the first volume should be issued in early December, and the next one in a couple of months. There are several parts in these books. We address everything almost from emissions to impacts on both precipitation, chemistry, and climates, and health and ecosystems. Nikos has coordinated 2 of these parts, and Maria as well. So I will stop here and let some time for questions. Thanks for your attention.
Thank you very much, Francois. I think CHARMEX indeed it was an excellent initiative for the Mediterranean, and hoping that we'll have in the future also more initiatives like this, because the area deserves specific attention. So questions, please. I don't see any question. Just a very rapid question, Francois. I was amazing, but this picture that you show the existence of particles, of dust particles with increased diameter. Any explanation for their presence?
Our hypothesis is that this is due to probably electrical fields, electrical charges. You know that emissions during dry conditions in arid areas produced electric charges, and this is probably conserved in some conditions. And we could derive this because we measure the noise of our OPC during the flight. And we observe that in the dust plume, we have a much stronger noise, and which is probably due to electrical charges. And we assume that these electrical charges counterbalance the gravitation.
And there is, on the same topic, a question from Joost Lelyveld. If the observed fine mode dust, aerosol, how you are sure that this is indeed dust?
Okay,
for the fine mode.
Yeah, I didn't tell you that this this OPC has 2 channels. It measures the near forward scattering and side scattering, and the near forward scattering is mostly insensitive to the nature of particles, when the side scattering is sensitive to it. So making a ratio between the scattering by the 2 channels, we are able to kind of classify the particle nature. And it's quite clear that in the dust plume, the signal is typical of mineral dust, even for the smallest ones.
Okay, thank you very much, Francois, for this very nice presentation, very interesting presentation. And now we move the next invited talk at Stratos Boutsoukidis. He will talk about non-methane hydrocarbons in the East Mediterranean and Middle East region. Stratos, you have also 15 minutes and the floor is yours.
Thank you very much. So yeah, my name is Stratos Boutsoukidis and I'm a recently recruited faculty member here at the Cyprus Institute. And today I will be talking about non-methane hydrocarbons in the Eastern Mediterranean and Middle East region, showing you some results from past campaigns, but also from current measurements, and also showing you our future plans in the research center. So why we are measuring and we are focusing on non-methane hydrocarbons, as you all know, in the presence of sunlight and with the intense NOx that are in the EM region, we are concluding to have quite high ozone production that, according to this picture and this review studies, has been shown to get increased in the recent years. Besides that, the non-methane hydrocarbons are excellent source and sink identification places, so we can distinguish among multiple sources that are currently 15 in our global emission models, and we can also define the oxidative history as they can be used as oxidative history markers. Here in KRC, we are planning to perform a wide range of measurements in order to identify both the source and the sink of non-methane hydrocarbons in order to further improve our atmospheric models. I will start the observations part with the Akaba SIF campaign that was organized and conducted by the Max Planck Institute for Chemistry a couple of years ago. And I was participating in this campaign, and I was measuring a large suite of alkanes, alkenes, and aromatics across along the Arabian Peninsula, where we were expecting to have a diverse non-methane hydrocarbon composition. And indeed, that was the case. In this overview plot, you can see the 8 different regions, and you can recognize that many of these species were having orders of magnitude different concentrations along the path. So as I said, we can use non-methane hydrocarbons to identify the sources, and an excellent example is dependent isomers. So in this plot, I'm showing you the relationship between N-pentane and I-pentane, and with the dashed lines is the literature-derived slopes, so the relationship between the pentane isomers. Inside the Arabian Gulf, we were measuring some ratios that fit quite nicely to their own natural gas, while inside the Suez Canal, we were measuring similar ratios as have been reported in the Texas Ship Channel, and similarly when we were stationed on the Jeddah port. Apart from the sources, they can also be used for defining the radical chemistry. And we are doing that by applying some oxidative triangle chemistry. So what I mean by that, you can see in this plot the reaction rate with OH and the reaction rate with chlorine. And you can see that this pair here, the butenes, have the same reaction rate with OH, but different reaction rate with chlorine. And the opposite for the other pair of propane and butane. So by plotting the ratios of these species and assuming an emission point that it's, for butenes, at least it's widely established that we are close to reality, then we can simulate the chlorine chemistry, the OH chemistry, and then we can define where we are. As expected, also I would like to note here that from these calculations, we have derived a very simple relationship that when using the slope of these ratios, then we can define what type of chemistry we are having. As expected, the chemistry in the EMER region is mainly dominated by the hydroxyl radical. But what was not expected, and this is where I want to go a bit to another part, which is the sources, is the following story. So in this plot here, I'm showing during the first leg and the second leg of the campaign, and their comparison between the measurements and the model. While the model was performing relatively well for the most of the campaign, there was one specific area named the northern part of Red Sea, where we saw stronger than prediction of several alkanes. For ethane, it was a factor of 20. For propane, it was a factor of 40, and so on. Interestingly, none of the known sources in the model could explain these high hydrocarbon measurements, and therefore we have applied a positive matrix factorization analysis to define the signature. So we got 4 different chemical signatures for the region, and interestingly, one of these was very high in light hydrocarbons. It was having the absence of anthropogenic influence, and it was independent of wind direction in their trajectories. Furthermore, it was having an exponential increase and correlation with sea air exchange mechanisms and therefore we have concluded that the Red Sea deep water is the source that we were looking for. Putting this source in our model, we can see how the measurements were comparing before the application of this emission source and how they were comparing afterwards, which means that this source can explain now the observations. So what this source is, we are not yet sure. It could be seepage from a leaking seafloor because the tectonic plates are colliding in this region. It could be from hydrocarbon-rich brine pools, or even from leaks from oil rigs that are located in the Gulf of Suez and the Gulf of Aqaba. What is most interesting here is to see the strength of these emissions, which is comparable with the emissions of entire Middle Eastern countries. Seeing a bit the implications, these emissions, and as I say, in the presence of nitrogen oxides in the atmosphere, they are reducing the most important atmospheric radical, the hydroxyl radical, while down with the emissions, they are increasing the tropospheric ozone production, and they are affecting the complete EM region regarding the PAN production over larger areas. So what we would like to do here at KRC, we would like to continue this job, and this is why I'm starting from a campaign that we have conducted again with Max Planck back in 2014, when we were measuring at the western part of Cyprus, and we were monitoring mainly aged pollution from Europe. There you can see that we were measuring alkanes and aromatics, and what I would like you to focus here is the extremely low concentrations here that were in the lowest PPT range, seeing that we have some tropospheric background and what was the influence of these air masses originating from Europe. As the next step, what we would like to do in the upcoming weeks is to employ our mobile laboratory and station it in the eastern part of Cyprus this time, in order to monitor the chemical evolution of oil and gas operations and related emissions that, as expected, they will be coming during winter time. They will be coming from Middle East. But until then, we have this collaboration with Valerie Go and the LSE and the joint PhD team. So we're making the same measurements here at the Cyprus Institute in the top floor. You can see the same figure that I showed you before, but this time with the data that have been obtained during the past months. As expected, we were having a big cluster that was fitting very nicely in the urban range. However, we also have a cluster that is not fitting to any of the ranges that we were expecting. And therefore, this is already a quite interesting result to understand and identify the source of this signature. Furthermore, I would like to show you some measurements that have been conducted by Aliki Christodoulou, which is in the frames of a joint PhD team with the University of Lille. She was measuring in Cairo, and here I would like to show you only the GCFID measurements of benzene and toluene, which are having some exceptionally high concentrations, up to 30 ppb for toluene and 10 ppb for benzene. And of course, this is again a work in progress, trying to identify the sources by applying positive matrix factorization analysis together with aerosol data. Looking a bit in the near future, in next December, we are having a collaboration with the National Observatory of Athens and the University of Crete, and we are planning to measure the chemical composition during winter time in Ioannina city, which, as you may see from the photos here, it is highly polluted due to biomass burning. So for this campaign, we will employ the mobile laboratory of National Observatory of Athens and place our measurements inside the kindergarten school. So it would be quite interesting to also make some additional measurements for the indoor air quality and health implications of this phenomenon. A bit further,
give us 5 minutes, please. 5 minutes. Thank you.
Thank you. A bit further in the future, and particularly in spring 2022, we are going to Qatar, and particularly in Doha, aiming to quantify the traffic emissions in the greater area and characterize the regional non-methane hydrocarbon background. These measurements will be conducted in close collaborations with the Qatar Environment and Energy Research Institute, where our colleagues are making intense efforts to understand the local and the regional air pollution sources and help to inform policy developments in order to mitigate the impacts on human health and ecology. And therefore, they have placed several stations across Doha, which will be used in order to make also our observations on non-methane hydrocarbons. But additionally, we will be measuring volatile organic compounds as a whole spectrum. As we very recently we have a new recruitment, we received a proton transfer reaction time of flight mass spectrometer here at our institute that has the great potential to monitor the complete spectrum of volatile organic compounds. You can see here in this plot how many peaks. There are hundreds of species.
I don't know, something went wrong with Stratos. I don't know what happened, but with Stratos. Pieradonius, can you hear me?
I think we lost Stratos. He was offline, but now he's online.
I am back, I think.
Yes.
But
Okay,
I
can
don't know.
you wrap up Stratos? Yes.
I don't know where the connection has been lost, actually, to be honest.
At the Qatar campaign.
Oh, okay. So after the Qatar campaign, so wrapping up is that we have recently, can you see my screen? Not really, yeah?
Yes.
Wait a minute. So can you see my screen now?
Yeah, yeah.
Okay, I'm sorry for this technicality. It was not up to me, obviously. So what I would like to show you as the end slide is that we are having a new recruitment where we have a proton transfer reaction mass spectrometer that will be applying in both campaigns, and it's capable of measuring the complete spectrum. And also I was saying that we are currently having a call for postdoc applications to work with this instrument. And of course, which is quite important, this one to thank the team of Cyprus Atmospheric Observatory. And here it's a photo from our latest station at the top of Troodos Mountain. Thank you very much, and my apologies for these technical problems.
Yeah, it was not your your fault. So thank you very much, Stratos. Really, really very interesting and exciting presentation. We're looking forward to do some work together. Unfortunately, due to this delay, I can take just one question. You have questions from the audience? If not,
we have two questions, Nikos. I have sent it to you. If you cannot see it, I will just make the question. The first question is, do you have any guesses of the origin of the sources causing the lower ratios of pentanes?
In the lower range of pentanes?
In the lower ratios.
There is also some background noise, Andre, that I cannot.
Yeah, and the other question?
The other question is, what about possible contributions from vegetation in the northern Red Sea?
I would assume that this is not the case because in general the wind. So the only big source of vegetation over there is the delta of Nile, and so we didn't have air trajectories passing from there. And the other origin of potential vegetation would be considered the phytoplankton, which again, the northern part of Red Sea is particularly interesting, that has very low amount of phytoplankton, close to zero, in contrast to the southern part where phytoplankton is much more abundant.
Okay, so thank you very much, Stratos, again. And now
Thank
we
you very
move to
much,
the oral
Andre.
presentations. To remind you, you have 7 minutes and 3 minutes for question, 2 to 3 minutes for questions. So we start the first presentation by Michalis Pikridas. He will talk about regional background sources of submicron organic aerosol in the Eastern Mediterranean.
Okay. Can you see my screen?
Yes.
Excellent.
Put it full mode. Yeah, please.
I'm trying, but okay, now I got it.
Okay, very good. Okay.
Dr. Pikridas, change also your display settings, please, because we can see your follow-up slide.
So, better?
Perfect. We can see full screen and we can hear you well. Thank you.
Excellent.
Okay, great. So, I will present mostly on one background source of submicron aerosol range in the Eastern Mediterranean. Most of you are aware that Cyprus lies at the intersect of 3 continents, Europe, Asia, and Africa. What you may not be fully aware is that the air mass origin dictates PM levels, but also the chemical fingerprint of the air masses that reach the island. Also, what I would like you to keep in mind, that about 10% of the air masses that reach Cyprus come from the Middle East, as I don't know if you can see my mouse, which is shown here, and also in about 9% air masses come from Africa. We measured at Ayamarina Xiliatou, which is at the center of the island. It's a remote site, starting from March 2015 until January 2017. And this is the seasonal pattern from our chemical composition of submicron aerosol. What I would like you to note is that sulfate and organics maximize during summer, and basically that the dominant component is organic, unlike other sites, namely Phenocallia in the Eastern Mediterranean, where the dominant component is sulfate. We try to identify what are the hotspots of these chemical components that we measured. So we did some inverse modeling. And we noticed that the organics and BC have the same hotspot area, which is the Middle East and West and East Turkey. While for sulfate, the hotspot is Greece and East and West Turkey. We went one step further, and based on these measurements, we managed to do a source apportionment study. Again, at the Ayamarina, we identified 4 factors: a biomass burning factor that was periodic, so I won't go into details about it, and 3 more which were persistent throughout the 2-year study period. For the HOA, for the one I call HOA, there was a small gap. So so we identified 3 factors: the more oxidized oxygenate organic aerosol, which the profile of which is in the upper left graph. Just below it is the less oxidized oxygenate organic aerosol. And these 2 spectra are very typical of what you would find, let's say, if you went to Europe. However, if we move to the hydrocarbon organic aerosol, the one I note as HOA, which is in gray in the graph in the middle, it is very peculiar, basically because it looks like it comes from cooking. This is what a cooking organic aerosol would look like in the submicron range, measured by this technique. And this is surprising because we are in a remote site. It is also persistent throughout the 2-year period, so day and night. It doesn't make any sense. So we try to again to identify what are the hotspot regions for the sources that we sources that we identified. So we have Greece and West Turkey for the less and more oxidized oxygenated organic aerosol. But for the HOA, the one we are interested at, which had a very strange pattern, it is the one where the organics and BC had a hotspot. Now, the fact that organics and BC hotspot in the same area suggests that this is probably a combustion source. So I was keen to believe that this HOA, came from a combustion source. Also, there is a small, let's say, discrepancy. What I mentioned before is that we noticed this HOA factor throughout the 2-year period, while, as I mentioned in the beginning, only 10% of the air masses that come from the Middle East reach Cyprus, only 10% in the year. So it seems that the hotspot is in the Middle East, but there should be another source in proximity. So I try to find out what are the power plants around Cyprus. And here is a map showing coal, oil, and gas power plants. You see here in the Middle East, in Lebanon, Syria, Israel, what I call a wall of power plants, very close to the island. There is also a lot of coal-fired power plants at Adana, which is a very polluted area, but also there are 4 power plants in the island. And since they're the closest one, I wanted to investigate them. To check their footprint, I went into satellites and I checked the NO2, the columnar NO2. This is an average of 1 here. And I have noted the 4 power plants. I have noted their power output, their maximum power output. Now, what I would like you to notice that the ones in the north, even though they have a relatively smaller power output, their NO2 emissions are distinctively higher compared to the ones in the south. So this may be something that's worth looking for. Also, I noticed that my HOA source, the one here in gray, correlates quite well with particulate nitrate in the submicron range. This is very typical for more and less oxidized oxygenated organic aerosol, especially for the less oxidized, which is with blue in this graph. So this is the correlation coefficient. But sometimes the HOA showed better correlation with nitrate than the other two. And this is surprising. It's not expected, at least.
2 minutes, Dr. Pikridas, please. 2 minutes.
Okay. So this is the profile I got in Cyprus. This is a typical cooking factor. And you see the problem is here, the 55 to 57. We get a 0.55 ratio. Typical cooking is 0.38. And when you get it from fossil fuel, when your organics, this hydrocarbon factor, when it comes from fossil fuel, this ratio is about unity. So I went in the literature and find out if somebody else had noted something like this. And of course, so I uses the dot product against what I got and what reference spectra in the literature. I use the dot product, so this means the smaller the number, the better the similarity. So I'm very interested in this part for the HOA, which is blue. This included several cooking factors, of course, but also SOA from diesel exhaust. Especially, there was one study that I got almost a perfect match. And this is a study from diesel exhaust done by Seiz et al. In these graphs, the blue is what I have come, the spectra that I have from Cyprus, and the reference spectra from the paper is in with brown. So, and this was unfortunately the only case that I managed to get this agreement. While in most cases, in most studies, this is what you would get, a ratio of almost 1 between these 2 peaks. So I contacted the authors of this work and asked them, what is so special about your diesel exhaust? Why it doesn't match everything else? And what they told me is that our engine wasn't working optimally. It emitted a lot of NO2. A lot of the diesel came out unburned. So it was a very, very bad engine, badly tuned engine. So to summarize, we have a hydrocarbon organic aerosol source specific to Cyprus identified. Hotspot is in the Middle East, but only 10% of the air masses come from the Middle East. So there should be another source which is closer, and I believe it's the 2 power plants in the north. And this specific source profile may result from combustion engines were operating under non-optimal conditions.
Dr. Piquedas, you need to wrap up, please.
I finished.
Good.
Okay. Thank you, Michalis. Any question? I cannot see here, but I don't know if there is a questions arrived to Andy, to Andrea.
No, there are no questions so far.
Okay. So, Michalis, you believe that this source of HOA has to do with local sources. Have you tried to see, recently there is work from the group of Pandis. They did in the chamber a lot of experiment with meat, by cooking meat. So, and then they have much better spectra from cooking. I don't know if you have already checked with this spectra to see also possible similarities. Because I know here in Cyprus, food also is it's a custom.
It is a custom, but the problem is I cannot believe that there is a cooking factor persistent for 2 years, day and night, midnight, 2 o'clock at night, 12 o'clock at midday. Persistent.
No, I agree, but could be a mixture.
Also, yes, that partly this factor includes some cooking. I'm absolutely sure. It's very difficult with this technique to deconvolute, but also
you
wouldn't get, actually it's here, you wouldn't get a hotspot in the Middle East. So I don't think this is a cooking factor. This is most likely a combustion factor, and it is because it is an unconventional combustion factor, as I mentioned. It is very hard. It is. I'm still trying to find ways to support it. But this is also the ratio.
I see.
I can check also the ratio with the work of Pandis. But
Okay, thank you very much, Michalis.
One last question, if we have some time. What are your next steps in your analysis?
Oh yeah, I was ready, but okay.
The next steps in the analysis. Yes, I will try. I would like to have some gas phase measurements and see whether this signal comes. What is the how to say? How much processed is this HOA? Because this will tell me whether this is in proximity and where from, with chemical clocks. This is what I have in mind. So basically,
thank you very much, Michalis.
How far the source is. Okay.
Okay, Michalis. Thank you very much. Thank you. Now we move to the next presentation by Dr. Dimitris Kaskaoutis, National Observatory of Athens, assessment of the spectral absorptions by black and brown carbon for different sources, application in Athens. Dimitris, the floor is yours. 7 minutes.
Hi, welcome to all. Do you see my screen? Because I had an issue.
Yes, we see your screen, but put it at full mode.
Okay, yes, that's great.
Presentation mode.
So here we present a technique that we newly developed about assessment and the convolution of the spectral absorptions by black carbon and brown carbon for different sources of aerosols and we applied that in Athens and in Ioannina during winter time. Scope and objectives of this work is a development of a new approach using a combination of common assumptions for the differentiation of the spectral absorption coefficients from ethanometer measurements into 5 components related to black carbon and brown carbon, and for sources like fossil fuel combustion, biomass burning, and secondary organic aerosol formation, the absorption of all these components. And this is recently published in Science of the Total Environment here, and that's the graphical abstract of our paper. And the convolution of the 5 components of the 5 absorption coefficient components to the total aerosol absorption inferred by the ethanometer measurements in Athens. Here is the methodology and the flow chart of our work, how the total measured absorption by ethanometer can be deconvolved to 5 components here. We apply the ethanometer model with angstrom absorption angstrom exponents for fossil fuel combustion and black carbon. We took the pair of 1.18 and 2 respectively, and we applied the brown carbon model, considering that the angstrom, that the absorption angstrom exponent for black carbon is 1, and there is no absorption from brown carbon at 880 nanometers and beyond. And using this approach, we calculate the fossil fuel absorption and the biomass burning absorption, as well as the black carbon absorption, the brown carbon absorption, and combining all these and the absorption angstrom exponent values, we calculated the spectral absorption coefficients related to black carbon for fossil fuel, black carbon for wood burning, brown carbon for fossil fuel, brown carbon for wood burning, and secondary absorption due to secondary brown carbon, which was estimated using the minimum R square method based on this equation here. Separately for daytime and nighttime conditions in Athens. At the left, at the right part, there is the approach how we estimated the absorption, angstrom absorption exponents for fossil fuel and for wood burning conditions in the Athens atmosphere by regression analysis between the biomass burning absorption coefficient at 950 nanometers with the MZ60 fragment from ACSM measurements. And we took the pair, we selected the pair 1.18 and 2 for fossil fuel and biomass burning angstrom exponents respectively. And here we present the results, application in Athens during winter time conditions, December 2016 to February 2017 for 3 months for nighttime and daytime observations. And we can see how this technique differentiated the 4 spectral absorption components due to black carbon in the gray colors and brown carbon in the wine brown colors, as well as a small contribution from secondary brown carbon during winter nights, mostly during winter nights. And in the right part, we present the fraction at 370 nanometers daily and daily, nighttime and daytime observations of the contribution of each absorption components to the total aerosol absorption. Note here that from the spectral figures also that depending on the wavelength, the percentage contribution of each individual component significantly differs. And at 370 and 470 are the most suitable wavelengths in order to see also the influence of brown carbon and wood burning absorption parts.
2 minutes, Dr.
Here,
Kaskaotis, please. 2 minutes.
yeah, here is the absorption fraction at percentage according to the wavelength, the diurnal variation in Athens, as well as the percentage contribution, and comparison with other components show that our estimates work well, since the FF, the fossil fuel components, are highly related with NOx and HOA components, as well as high correlation between the biomass burning absorption components with CO, organics, BBOA, delta Z, non-salt potassium, which are BB tracers. And we applied the same in Ioannina for the campaign that we did in December 2009 to February 2012. We found here very large fractions and contributions from brown carbon as well as black carbon wood burning aerosols. You can see these two parts highly contribute to the spectral absorption as well, and this in the right is the absorption coefficients on 370 nanometers due to the diurnal variation of them in Ioannina, with a large contribution of wood burning emissions during night time. And conclusions, we presented this technique for 5 absorption components related to the absorption of black carbon and brown carbon separately for fossil fuel combustion and biomass burning. We made some assumptions for the absorption angstrom exponents for fossil fuel and biomass burning according to the literature. And we applied initially this technique in Athens and Ioannina. The results were very promising at both cities, and we also performed sensitivity analysis and analytical description of the uncertainties in our publication. And this with hope that they can be easily applied to any environment over the globe that has spectral absorption measurements. Thank you very much.
Thank you very much, Dimitris, for this interesting presentation. Questions? Okay, so this means that under wood burning, you have contribution from brown carbon, which is highly significant compared to the black carbon, which is almost 70% at the two, both these two fractions at the low, at the 370.
Yeah, that's right. I tried the same for a summer period when biomass burning and the component of brown carbon is much less. It works also properly in view of errors and uncertainties, so we do not have large differences compared to the winter season, but the components there were very less.
Yes.
So nearly the 90 or 95% contributed to fossil fuel, to black carbon from fossil fuel combustion. So I think that even you will apply that in a place that you have significant contribution either from secondary organic carbon or from biomass burning sources. Or if you don't, you may choose some winter periods with larger contributions from a residential.
Yes. Okay, Dimitris. So, Andrea, there's a question, a rapid question.
Yes, I have assigned you one, Nikos. Yeah. I don't know if you have seen it.
Yes,
if not, I will send.
No.
I will. Okay. The one question we have, Dr. Kaskaotis, is could you address dust as an additional component?
Well, very good question. About dust.
Please repeat it, because I checked the chat, it was there and I missed it.
No. It's in the question section. Could you address dust as an additional component?
We did that at the Ioannina and in Athens based on calcium component that we have from ion chromatography. There is also some works in the literature that tried to do to deconvolve this dust component, but we find it very less than in Ioannina, especially during winter time, less than 1%. So we did not took it into account, and 1% it was not spectral average, it was at 370 nanometers. At the other nanometers and longer nanometers it was much less, so did not take it other account. Just for information of the panel, work in Tibetan Plateau, not like this, but the convolution of brown carbon and dust components against black carbon, only these three components, estimated a dust contribution at shorter wavelengths about 5 to 7%, even in a place that they do not have urban emissions. So especially in urban areas, the contribution of dust is to the absorption components is very less.
Okay, thank you very much, Dimitris. So if somebody has questions, they can contact you. Yes. Okay, then we move to the next one, characteristic of new particle formation in Cyprus by Rima Balbaki, University of Helsinki.
Thanks, Nikos. I'm wondering if you can see my screen already.
Yes, yes.
And, okay.
Yes, now we can see full screen and we can see you and we can hear you well.
That's great. Okay, so thanks for the introduction. I'm Rima Balbaki and I'm a PhD student at the University of Helsinki. And today I will be presenting the results of our newly published study, which you can find in ACP. And it's basically characterizing new particle formation in the Eastern Mediterranean, mainly in Aya Marina and Cyprus. First, a little bit of introduction about why we're interested, or what is new particle formation. So it is the process by which low volatility gases, they condense to form molecular clusters, and then these clusters, they grow into bigger sizes of particles until they are climate relevant particles. And this process is important because it's a large source of particle number concentrations in the atmosphere. Okay. And in 2018, Yemen made an overview about all the studies of new particle formation across the globe. And you can see that the occurrence of this process, it's the annual frequency, it ranges between 10% and 70% in the sites. And if we focus on the EMME region, we can see, for example, in Fennocalia that the annual frequency is around 30%, whereas if we go to Had al-Sham in Saudi Arabia, the annual frequency is much larger. Also, I show here these two studies, and we can see also that the seasonal variation of this new particle formation occurrence is different in the two sites. So we're interested in doing more measurements in this region to understand how and when and what are the characteristics of new particle formation in the region. Okay, so now a little bit about the site of the measurement. It's Aya Marina, an inland site which is 500 meters above sea level. And what we know about this site from long-term measurements is that it is affected by high aerosol mass loading, and usually they are highest during the warm periods of the year. And in terms of dust, the dust is usually peaking. Sorry, I'm not seeing myself. Okay, and the dust is usually peaking in September and November. Okay. And in terms of the other pollutants, we know that there is a high ozone concentration throughout the year, which is usually because of the high solar radiations. And then in terms of CO and NO, this is a rural background site, so the concentrations are relatively low there. And here I'm also showing a short study, which was part of the Charmex experiment in March 2015 in the same site. And they showed that there is a mixture of both biogenic and anthropogenic VOCs, which they believe that they are contributing to this high concentration of sub-3 nanometer particles and to new particle formations in this site. Okay, so now about our study, we did 1 year measurements and we used a suite of instruments to measure the particle size distribution. And these instruments, they can measure particles from 1 nanometer using the AirModus nano condensation nucleus counter, and the AREL NAS, which measures both neutral and charged particles. We're also measuring the accumulation mode particles. Well, starting 15 nanometers, we're using the SMPS from 15 to 1000 micrometers. And for a very short period of time, we also deployed a CI Apitof just to be able to measure a sulfuric acid proxy, which is representative for this site. And now in terms of the results, first I'm showing the seasonal frequency of new particle formations. And you can see that this process is happening throughout the year, and it has sort of a bimodal distribution, peaking in the spring and in the autumn seasons. And now if I compare it to the Phenocallia site, we see that the seasonal variation is similar to what's happening in Phenocallia, but we see that the percentage of recurrence is higher in our site, and this could be due to that there is different chemistry going on, or maybe because of our instruments that we were able to measure this process from 1 nanometer in size. So we were able to characterize all these events which did not grow past 15 nanometers in size. And then I'm showing here a little bit of the surface plots of the particle size distribution to show that these events are happening, like it's not the same thing that is happening all the time. So in some cases, we have these regional events where the particles grow from 1 nanometer size and they continue growing wherever the air mass is changing. And we usually call this a regional event. And then we had certain days where we have multiple onsets of particle formation. We also have a lot of these local events where we see a burst of particles, but usually it doesn't exceed 15 nanometers in size. We also spotted some particle shrinkage events, and in some cases we had also these nighttime events. So in black here, you can see that the radiation was low, and then we see that there is particles growing during the night. And of course, it's also... Okay. And we also see that even in the cases where we had high dust in terms of PM10 and PM2.5, we were still having very high concentrations of these new particle formation events. And we usually like to, in order to understand how this process is happening, we usually plot the particle formation rate versus the sulfuric acid, because it's the main nucleating gas in the atmosphere. And we see that in this points here, they show that we are well above the sulfuric acid ammonia system. We are a little bit below the sulfuric acid ammonia DMA system. So we're still not sure which gas is the one that is stabilizing the sulfuric acid clusters. And then also we see that during the summer periods, or these points here in orange, that the sulfuric acid concentration was higher, but it didn't translate to higher formation rates. So sulfuric acid alone was not able to explain why new particle formation is happening or not. And then also with respect to the condensation thing, we see that MPF is occurring at various condensation sinks. So it's not the limiting factor for new particle formations. In terms of meteorological conditions, here in blue is the event days and the green are the non-event days. And you can see, for example, in the winter month that for temperature here is quite important, that when the temperature is higher, we see more event days. But during the summer months, which had the lowest MPF frequency, even when the temperature was high, we had the lowest MPF frequency. And this applies to the other meteorological factors as well. In terms of the gases, pollutants, the most interesting thing that we saw in these plots is that the MPF frequency is usually following the same trend of this of NOx and CO. And we don't believe here that NOx and CO are the main species that are nucleating, especially that the concentrations are really low, but we believe that they are sort of proxies of some anthropogenic emissions, or some anthropogenic emissions coming to our site from long-range transport. And then if we look at the air mass trajectories using...
Can you please wrap up with that, Rima?
Yeah, this is the last slide. So you can see here that during this month that had the lowest MPF frequency, we have it's mostly northerly winds coming from Europe, and the air masses are blocked from the Middle East region. So we believe that it could be that some pollutant important for new particle formation is coming from these places. And with that, I'd like to end. Thank you.
Thank you very much, Rima. You have a really interesting presentation for something which is very important for the area, this new particle formation. Andre, there is any question? I cannot see.
Yes,
that
there are two questions actually. The first one is, can you speculate on the stabilizing molecule?
Well, we definitely know that ammonia should play a role. We're still not sure what is the other one. So usually what we do is we compare to these chamber studies. And in my plot, I showed that the formation rates that we're measuring are a little bit below the DMA system, DMA ammonia system, but we're still not sure what is the compound. It could be DMA and ammonia, or it could be a mixture of these compounds.
Okay, the other one is, how do you define NPF events and their frequency?
So usually we plot the NPFs on a daily basis, and the surface plot would tell us when is NPF happening and when it's not happening. Not sure if I can go back. So I didn't show here a plot for non-event, but usually if you have a non-event, the spectra here will remain blue and you don't see this increase in the new particle formation. So this is how we define if a day is a new particle formation day or not.
Okay, and the last one, from in situ chamber experiments in the Western Med, it seems NPF could be related to marine emissions of iodine compounds. Any comment?
We still cannot say for sure if marine contribution is affecting or not. From our 10 days of measurements, which were in February, we have seen that we have measured iodic acid with a nice diurnal cycle, but the concentrations were quite low. They were below 1 e to the 6 molecules per centimeter cube, which is usually not it's not enough for iodic acid to be contributing to new particle formation unless it has some sort of synergetic effect with sulfuric acid. So we still need this long-term CI of measurements to be able to tell for sure if iodic acid is contributing or not.
Yeah.
Okay.
Thank you very much, Rima. I think it's a very important subject for the area, and for sure more work is needed. But it's quite amazing to see all this, the difference. But how often we have this new particle formation. Now we move to the next presentation by Dr. Stathopoulos from Douce, Greece. Satellite-based observation of aerosol cloud relationships under different water vapor conditions over the Eastern Mediterranean.
Thank you, Professor Michalopoulos. I believe you can see my screen now.
Yes,
okay.
Of course. Okay, so you can proceed.
Hello, everyone. I'm Stavros Stathopoulos from the Demokritos University of Thrace. This research was conducted with my colleagues, Dr. Georgoulias and Professor Kourtidis. The goal of our study was to study the annual and seasonal aerosol cloud relations under different water vapor conditions of the urban and rural subregions of the Eastern Mediterranean. So we separated this Mediterranean region into 9 subregions for land and ocean, and we aggregated those regions as well and called for land as a Eastern Mediterranean land region, and one for all the ocean regions as Eastern Mediterranean ocean regions. We use data from the QuadEAMS project, and specifically we used aerosol optical depth at 550 nanometers, fine mode ratio over C, cloud cover, water vapor, cloud optical depth, cloud pressure from MODI sensor on board Aqua. We also used aerosol index from TOMS and OMI satellites, reanalysis data of fine mode ratio over land, and reanalysis data from GoCard. And so we were able to separate the aerosol optical depth at anthropogenic aerosol and sea natural aerosol optical depths, following the methodology from Georgoulias et al. 2016. So we had a very big data sets, daily data set, and we wanted to separate them to anthropogenic data set and dust data set, and to find the retrievals of cloud cover, water vapor, and the cloud optical depth due to anthropogenic aerosols. We set the criteria that the aerosol optical depth of anthropogenic aerosols to be greater than 2 times of AOD of sea and natural, and at the same time to be greater 2 times of AOD from dust. So for those days, we use the corresponding cloud cover, water vapor, and the cloud optical depth data. We use the same criteria, the analogous criteria for AOD dust, and use the corresponding CC, WV, and COD data. So as far as for total aerosol optical depth, cloud cover, water vapor, cloud optical depth, and cloud top pressure data is concerned, we separated the cloud properties data into 0.1 AOD bins and 1 centimeter water vapor bins, and calculated the mean value of for cloud cover, cloud top pressure, and the cloud optical depth. As you can see, for constant water vapor, for increasing AOD, the cloud cover is increasing. Same for cloud optical depth, especially until AOD 0.5, where after that we see that the oddities remain the same, or in some cases it decreases. And we also can see that as AOD increases, the CTP decreases, probably a sign of cloud aerosol incorporation effect. To see the difference between the land areas and the ocean areas, we calculated the difference of our parameters, cloud cover, cloud optical depth, and the cloud top pressure. And we saw that even though we have over sea areas greater cloud cover, the cloud optical depth was lower overseas, as far as CTP is concerned, we have higher clouds over land. We did the same method. We used the same methodology for anthropogenic aerosols. The results were similar. For increasing aerosol, we have increasing cloud cover and COD, and we had higher clouds. Here are the results between ocean and land. Same behavior. We had over land, the clouds had more optical depth, and the clouds over sea were lower. And the same.
2 minutes, Dr. Stathopoulos, please. 2 minutes.
Thank you. And and for the dust data set, similar results as well. Increasing cloud cover with increasing AOD, and higher clouds as aerosols concentration increases. Note that the cloud optical depth cause of dust is smaller from the cloud optical depth that we saw because of anthropogenic aerosols. So, and this is the results between ocean and the land surfaces, similar patterns. So to conclude, we found that overall region, seasons, and water vapor bins, cloud cover was found to increase with increasing total anthropogenic aerosol and dust loading, pointing towards the aerosol incorporation effect on clouds. Cloud optical depth, especially for aerosol optical depth less than 0.5, was found to increase with increasing AOD, while for AOD greater than 0.5 to decrease or remain constant, it's irrespective of water vapor amount. The anthropogenic cloud optical depth was observed to be larger than that of dust. The cloud optical depth over land was found to be greater than the 1/c, respective of water vapor and the aerosol optical depth. And finally, for constant AOD and water vapor, clouds over land were found to be higher in altitude than over sea. Thank you very much for your attention.
Thank you very much, Dr. Stathopoulos. The really very interesting presentation, especially for the area where water is in scarcity, and so all the story of cloud formation is of great importance. Questions from the panel? Andrei?
We have not received a question so far.
Excuse me?
No questions so far.
Okay.
Okay.
So, thank you very much again, Dr. Stathopoulos, and now we'll move to the next presentation, which is a relationship between IronNet and Moody's-based aerosol optical depth with surface PM10 over Cairo, Egypt. And the presentation will be given by Ahmed Sarased from EMA, Egypt. Dr. Sarased, the floor is yours. We see your screen, but we cannot hear you. And if possible, you put it at full presentation.
Yes. Hello. Can you see my screen?
Oh, yes, yes, but not a full mode, because you see also the slides
now
closed,
it is in
so...
full mode. Now it is in full mode. We can
okay.
see it, we can hear you, and we can also see you.
Now,
so please
yes.
go ahead.
A problem. Okay. Can you see?
Yes, yes, you are ready to go.
Yes, and you can hear you, so you can proceed.
I am Sara Said. I am a meteorologist from Cairo, Egyptian Meteorological Authority. I represent the relationship between AeroNet Moody's based also optical depth with surface BM10 over Cairo. Scope of study the variation of one of the most. Can you hear?
Yes, we can hear you, Dr. Said. We can hear you. And we can see also the changing slides. So please proceed. The floor is yours.
I can't share my screen. It not appear to
Yes,
you.
we see your screen and we can hear you. Yes, everything is fine.
Okay.
It's very good.
I know my screen. Scope of study is the variation of the most important pollutants of affecting air quality in Cairo, particulate matter with diameter BM10. By analyzing the coloration between BM10 coloration measured at Cairo and also optical depth from AeroNet and Moody's and Aqua satellite during 3 years from 2012 and 2014. Description, site description, and data description. Cairo is Egypt's largest urban city, around a third of population in the greater Cairo. Data description. I used the BM10 mass concentration, surface BM10 mass concentration. Our surface BM10 mass concentration data were obtained from Egyptian Meteorological Authority, and I used the AeroNet from NASA and the Moody's satellite Aqua and Terra. The figure show the relationship between AOD from MODIS satellite and the Terra satellite and from Aeronet. We can show that the result indicates that the monthly mean of AOD data from Aeronet and the MODIS for Cairo, Egypt is between 0.2 and 0.5 over Cairo most of the year. And the most of year monthly AOD value relative high greater than 0.2. The maximum AOD showed in spring season, then in autumn season, and the minimum AOD for Cairo is observed in winter season. If we show the correlation between Aeronet and the BM10 concentration over Cairo, we can show the good correlated between them and are equal 0.8 and 6. And when show the correlation between BM10 concentration over Cairo and the MODIS satellite Terra, we can find the good correlation between them and are equal 0.8 and 83. Correlated between the BM10 concentration over Cairo and the MODIS satellite from Terra is good correlated and are equal 0.84. To show the climatology of the seasonal aerosols change over Cairo through 3 years, we can find the maximum value of AOD is showed in spring season and then in autumn season, and the minimum in summer season and in winter season. This from Aeronet. To show the climatology of Egypt from satellite Terra and Aqua, we can find the same as the maximum value of AOD showed in spring season and then in autumn season, and the minimum is shown in winter season and in summer season. The conclusion is 3 years the measurement of BM10 over Cairo on daily, monthly, and seasonal used AOD to characterize and understanding of optical depths, AOD, and the pattern over Cairo. There was high correlation between good ground-based BM10 concentration from surface observation and the AOD from Aeronet and the MODIS satellite Aqua and Terra. The maximum of the AOD and are recorded in spring season because of the frequency of a dust storm associated with the Khamsin depression occur in Egypt, and in autumn as a result of stability of the atmosphere and the occurring of the burning of atmospheric waste. Thanks.
Thank you, Dr. Said. Professor Michalopoulos, over to you.
Yeah. Thank you very much for your really nice presentation about Egypt and the relation between optical depth and BM10. Andrew, we have questions from the panel.
And no, we have no questions.
Can you relate this these PM210 levels with dust and wood burning or traffic? Do you made any effort to separate the different sources of PM10 in Egypt? So how much dust contribution, how much is wood burning, and how much is traffic?
Yes, الدست is نتيجة climatology of Egypt. Traffic is due to publication. فالدست نتيجة climatology of Egypt from desert, western desert and eastern desert affected on the climatology of Egypt.
Okay.
Professor Michalopoulos, we received 2 questions.
Okay.
The first one is, did you look at some of the outliers of the AOD?
Yes.
Again?
Did you look at some of the outliers of AOD?
In summer?
Yes.
In summer?
Outliers.
How you can explain the outliers of AOD?
I don't hear. Again.
Andre, can you repeat slowly, please?
About the outliers of EOD. Did you hear me?
500 nanometer.
Let's move on to the next question. Is this work published?
Yeah. If this?
Is this work published?
Yeah. Have you published these results? Have you already published these results? Is there any publication?
I am still doing on it.
Okay. Thank you very much.
And one last one.
Yeah.
One last question. Can you speculate on some of the reasons for high concentrations in the observations?
Any idea about the origin of the high levels that you see? Any idea? Do you have any idea? What is the reason for the high levels?
Concentration in Egypt?
Yes, for the high levels. Yes. How you can explain the high levels that you see in Egypt? Is dust, as I said, is dust, is wood burning,
dust,
or?
Dust. The first reason is dust climatology of Egypt from dust الخمسين depression in spring season affect in high concentration of dust in Egypt. The mainly reason is climatology of Egypt.
Okay. Thank you very much.
Yes,
Dr.
3 minutes
Said,
have
and
passed,
then
Professor Michalopoulos. We need to move on.
And then
please.
I think, yes, no worries, Spyridonous. We have just one presentation. I think we are on time for the lunch break. So we move now to the last but not least presentation from Dr. Paisi. Premature mortality from exposure to avian PM2.5 black and organic carbon in the EU27.
Okay, hello everyone. Do you see my screen? Or...
Yes.
Okay. Just a moment.
The screen, we can hear you, but just put the presentation at okay, now it's excellent.
Okay, hello everyone. My name is Niki Paisi. I'm a PhD student here at the KRC Center of the Cyprus Institute. And this presentation will be about the premature mortality from exposure to ambient PM2.5, black and organic carbon in the European Union. So air pollution is the fourth top risk factor associated with the highest number of deaths worldwide, and it causes comparable losses of healthy life expectancy with that from tobacco smoking. And although air pollution in most European countries has decreased over the last decades, in many parts of the region, especially in large capital cities, it remains above the WHO safe limits. The southeastern Europe, including parts of the eastern Mediterranean Middle East, as many of you may know, is a hotspot of not only of climate change, but also of air pollution. So the objectives of this study was to estimate the premature mortality which is attributed to outdoor air pollution specifically from PM2.5 using the WRF-Chem model, and then to estimate the fraction of this mortality from the carbonaceous components, taking also into account their differential toxicity. We used the WRF-Chem model, which is a weather research and forecasting model coupled online with chemistry, which means that it simulates meteorological and chemical processes at the same time. And we applied this model to simulate the atmospheric composition over Europe based on the year 2015, focusing mostly on PM2.5 and its carbonaceous components. The model setup, in the initial and boundary conditions were obtained from the global models. All anthropogenic, biogenic, and dust emissions were included. The resolution of the simulation was at 20 kilometers, which is quite high for a region that covers the whole Europe. The chemical mechanism which was used was the Russian chemistry coupled with made volatility basis set aerosol scheme, and the simulation was performed at the CYI HPC facilities. At this slide, I will explain the methodology. So the premature mortality was estimated by using the global exposure mortality model. This is a risk model provided by Burnett et al., which estimates the excess risk of death from exposure to PM2.5 from non-communicable diseases and lower respiratory infections, which includes all those 5 diseases, also reported in the global burden of disease study. And it's compared to a counterfactual concentration of 2.4 micrograms per cubic meter, under which we assume that there is no risk of death. So what we did is to estimate the graded annual average concentration of PM2.5 for the year 2015 with the RRF chem model, and added this information in the risk model to estimate the premature mortality from PM2.5 by combining baseline mortality rates and population data, age-specific, with the hazard ratio. And then we repeated also the calculations by using PM2.5 concentration without the black carbon and organic carbon. And then to estimate the fraction from the carbonaceous components, we subtracted the second equation from the first one. However, carbonaceous PM2.5 components are more toxic than other inorganic ones based on many toxicological studies. So what we did was to assume that these are twice more toxic and repeated all the calculations. And here the graph shows, I added this graph just to show you the nonlinear relationship between the risk and the PM2.5 concentration, and that it's age-specific, but also disease-specific. And the results, the total premature mortality in the EU27 is estimated to be 392,000 excess deaths from PM2.5, and the fraction from black carbon and organic carbon is 70%. When we assume a double toxicity. But when we assume unequal toxicity, then this lowers to 8%, which equals to 31,000 and 65,000 excess deaths, respectively. And just to pick up some countries of the...
2 minutes.
Yes. In Cyprus, we have 415% from black and organic carbon. In Greece, 7,200 from PM2.5 and 23 from black and organic carbon. On the right-hand side, you can see the graphs of the absolute number of deaths per country and the percentage of that attributed to black and organic carbon. And here I have added the normalized premature mortality. As you can see, in Eastern European countries and in Central Europe, the mortality is quite high from PM2.5, and the percentage attributed from black and organic carbon, for example, in the Eastern Mediterranean region, is around 10 to 30%. And the conclusions, the toxicity of black and organic carbon is still not well quantified, and this affects the mortality estimations. So we don't know if it's twice or 5 times more toxic. Most of the times, probably the mortality is underestimated. Our sensitivity analysis shows that the assumption of a double toxicity increases the total premature mortality from PM2.5 by almost 9%. And we suggest that the countries with high concentration of these particles would gain much in terms of health benefits if air pollution mitigation policies would be source specific. And with this, I would like to thank you for your attention.
Thank you very much, Ms. Nikki Paisi. A really interesting presentation regarding the health impact of the aerosol, and especially black and organic carbon. We can take few questions. Andrei, you have any questions?
Yes. Finland looks a special case. Can you comment?
in the table where, sorry. So Finland, yes, it's quite a large country. Here we have the absolute number of this, so the population is high. The black carbon here is, the contribution of black carbon is also quite high because there might be a large contribution from the residential sector, from wood combustion for heating and cooking, for heating mostly. So yes. Did I answer the question?
Okay, let's go to the next one. Do you know why BCOC might be more toxic than, for example, ammonium salts?
Studies suggest that combustion derived particles are more toxic. Black carbon is very small in size, so it can deeply penetrate the respiratory system and also reach other organs through the circulatory system. It's mostly emitted with other particles, toxic particles like metals, and these are what these are also what they are doing. The metals are the toxic ones that causes oxidative stress, for example, and
Okay, one last question. Any plans to extend this study to the Middle East?
Yes, it would be good to study that region as well. Yes, it's in our future plans.
Okay, thank you, Nikki.
Thank you.
Okay, and please wrap up the questions if there are no more.
No, there are no more, I think. So I think we are very nice and on time, even 5 minutes in advance, unless if there's some other question from the previous
No, I
talks.
wrap up from you, Professor Michalopoulos, about the session.
No, I'm fine. Yes, okay. I think it was a really interesting session. We had very nice results. I would like to thank all the presenters for their interesting talks, presentations, and by keeping the time. And I think we can move for a lunch break for 1 hour. Am I correct, Pieradonius?
Yes, thank you, Professor Michalopoulos. We are indeed a little bit ahead of time, but then we have gained 4 minutes more for our lunch break. I will invite, first of all, I will thank you for chairing this, this session. And I would like to invite all of you back at 2, so in 1 hour and 3-4 minutes, at 2 Cyprus time, for a session on atmospheric dust, which will be chaired by Professor Franco Marenko. So at 2, please, Cyprus time, please be back here for the session atmospheric dust. Have a nice lunch break to you, or dinner break according to your time zone. Be back at 2 Cyprus time. Thank you very much.
Yes. Bye.
Dear colleagues, we will start again in 2 minutes from now. In 2 minutes, please. Thank you. Okay, dear colleagues, so good afternoon or good morning or good evening, depending on your time zone. Thank you all for coming back to the continuation of our first day of our workshop. I will just remind you very quickly a few logistics. Please keep in mind to use our hashtag for the social media. So it is hashtag EMME4 with the number climate for your posts and your likes and for sharing how successful we are. We have been this far. I would also like to remind you that for the sessions, we have one chair for each session. And then this chair is responsible for calling out the sequence of colleagues, speakers presented. Each session has invited speakers who will present for 15 minutes, 15 minutes, followed by 5 minutes questions and answers. And then oral presenters and their presentations will have a duration of 7 minutes with a follow-up Q&A of up to 3 minutes. So without further ado, yes, I'm getting reminded also that I should remind you that please, for your questions, use the box which you can reach by going to the to, and then you select, you scroll all the way down and you select send question to staff, and then we will make sure that we have the question for the chair and for the particular speaker at the given time. So thanks again to our support for that. Now, without further ado, I would like to invite, for chairing the session on atmospheric dust, I would like to invite Associate Professor Franco Marenko. So please, Professor Marenko, the chair and the floor is yours.
Thank you, Pier Antonio. Welcome everyone to the dust session, which we have this afternoon. And without further delay, I will pass the floor to Dana Francis from the UAE, from Khalifa University, who is going to give us a talk about dust storms in the MENA region, atmospheric drivers, characteristics, and impacts. Dana, the floor is yours.
Hello, everyone, and I'm very honored to be with the community today to talk about the atmospheric dust in the MENA region. And I look forward to interesting exchange within the community. So I'm going now to share my presentation. I hope you are all seeing it.
We see clearly and we hear clearly. Please go ahead.
Perfect. Okay. So dust storms in the MENA region. Today we will learn a little bit about the atmospheric drivers, the characteristics of these dust storms, and their impact. Here I'm showing a global map of all natural aerosols that can be found in the atmosphere. And among all these natural aerosols, we can see clearly that dust, which is in the red and orange colors, is the most important type of natural aerosols in terms of mass that we can find in our atmosphere. And we can also clearly identify that the MENA region is the main contributor to this dust load in the atmosphere. So just trying to move this from my screen. Yeah. Why? Because the Middle East and North Africa region is actually home to the largest dust source on Earth. As you can see here in this map derived from satellite observations, where the major sources are located in the Arabian Peninsula, in Southwest Asia, and in West Africa and North Africa. And this contribution to the global dust emission is estimated to up to 60% if we sum up Africa and Asia together. This is both in the AOD, which we measure in the total column, atmospheric column, and also from the dust concentration at the surface, as noted by these recent studies on the contribution of each dust source to the global estimates. So where are these dust sources located? If we zoom into the region here, we can see first that they are located in low-lying areas, and also they have a frequency for activation, which then will depend on the atmospheric patterns. We can also see that there is a zonal increase in meridional increase in the dust activation frequency, meaning that the major sources are located around 20 north, both in the Arabian Peninsula and North Africa. So, the take-home message here is that the main annual contribution to global emissions is up to 50%, which is quite considerable, and require from us a deep understanding of the dust cycle in this region. For example, we have seasonality in dust storms in the MENA region. If we look at deposition and emission fluxes year-round, we can clearly identify that spring and summer are the most active seasons, and this also valid for the lifetime of dust in the atmosphere. So we can see here the peak in spring and summer, as well as for the lifetime of aerosol dust in the atmosphere being in summer and spring. Of course, there are some activity also in winter and less in fall. So what about the trends? What we know for the trends in dust activity in the region? It's not yet clear actually how the dust activity is behaving over decades. If we look at the last 2 decades, we had kind of contrasting behavior. So from 2000 to 2010, we had dust emission and concentration increasing over the Middle East by 15% per year, whereas we observed a decrease over North Africa and the Sahelian region here. And these are derived from satellite observations as well. Whereas for the period 2010 to 2020, we noticed that this activity, both of them are recovered toward their climatological means, with even decreasing tendencies over the southern Arabian Peninsula. So now, bearing in mind these facts and these uncertainties that we are seeing regarding the dust activity, it's important to know that the atmospheric patterns are very essential for any dust activity, because we have dust sources, but these can't be activated unless there is a forcing or a trigger which comes from the atmosphere. For example, each region can have dust emission or not, depending on the meteorological conditions and depending on the season as well. As you may notice here, the MENA region is located in the subtropical zone, and therefore it's influenced by weather patterns from mid-latitude as well as from the tropics. So what I'm showing here is a summary actually for several studies on identifying the atmospheric drivers for dust emissions in this region, depending on the season. So here I'm showing for winter and spring, mainly the background winds, which are Harmattan over Africa. We call them Shamal winds over the Arabian Peninsula and Livar winds over Iran and Pakistan. These are present year-round, and they form over desert region because the rapid cooling of the desert surface during winter and spring. In addition to these wind patterns that are usually present, we can have episodically formation of cyclones, which emit a large quantity of dust, and these are the major contributors to dust transport towards Europe. And also we can have the occurrence of some colder front and intrusion of this colder front from the mid-latitudes toward the MENA region, and these also can have a spectacular dust emission. Here, for instance, I would like to explain a little bit the physical basis of the Harmattan and Shamal winds, which are low-level jet that forms during night over deserts. Why? Because the desert surface during winter, it cools faster than the air that is above it. So this creates a decoupling between the boundary layer and the surface, and therefore accelerating wind can form. We call it nocturnal low-level jet with high wind speeds. And after sunrise, the convection restart in the boundary layer, and these high momentum are mixed down to the surface. So in these areas and on an annual basis, we can see that the dust emissions occurs actually during morning hours. And here you can see how the low-level jet acts in surface observations. If you happen to have, for example, wind profiles, you can see the core of the low-level jet during night. And then if you compare it to surface wind, you see the peak in surface wind shortly after sunrise. And with it, the visibility can decrease. And here is the increase in the morning hours of surface winds. So this is very important to understand because until now, it's very difficult to simulate in models this phenomena. Here I'm showing an example of dust storm caused by colder front. These are easily identified in satellite imagery, such as Siberi, for example, and they can really cause massive dust storms. Here is an example about the dust emission associated with Saharan cyclones, or the cyclones that develop over North Africa during especially spring. This case was a bit unusual from what is expected because we noticed during this case that the dust transport was mainly toward Greenland and the Arctic instead of going toward the Eastern and South Europe and the Eastern and the Mediterranean. Sorry. So by looking at the circulation, we identified that the changes in the polar jet circulation that has been identified due to the loss in sea ice in recent years was mainly at the origin of this new pathway of Saharan dust to the Arctic. So I would like to explain in a few words. So here, if you have a normal situation where temperature gradient is very strong between the polar regions and mid-latitudes, the polar jet is going fast, and this pattern we can see it in normal situation. But few studies have been noticing in recent years that because of the Arctic warming and the loss of sea ice, the temperature gradient is less between these two regions, and therefore the polar jet is slower and is meandering. So we have more troughs, more blocking, troughs blocking. And when this goes over the Sahara, so the first trough will lift the dust, and then the second wave will bring it further north. So there is more.
5 minutes, please, Dr. Francis. 5 minutes.
Yes. So here, this is a new pass that it's caused by the changes in the polar jet, so we can directly transport the dust from the Sahara toward Greenland. And it can cause, of course, ice melt and increase in temperatures in the high Arctic. So this also can impact, we can see this pattern as well over the Eastern Mediterranean. If anyone of you remember this massive case of dust emission during the full month of September 2015, where a series of cutoff flow from the polar jet occurred over this area and caused a dry cyclone to form. And a few days after, with the second wave coming from the polar jet, a cutoff high was created. And this one caused convection and density currents again over the Middle East with massive emission of dust. This is how it looked from space, for example, and this from the ground, a really orange sky here in Abu Dhabi during this event. Now, if I move to the summer season, the main factor that is added during the summer season is actually convection, which comes with the monsoon season over this area, but also over the mountainous areas in Turkey and Morocco and the UAE. So why convection? Because from convection we can have a creation of downdraft. So these are cold pools, and they are characterized by turbulent mixing at their fronts, like density currents. So they lift a huge amount of dust as well if they occur over desert areas. But also dust emission during summer can occur due to some anomalies. Maybe many of you remember the June 2020 Godzilla dust storm, which lasted for around 10 days with continuous emission over Africa. And it was caused by the formation of a stationary high over this area, which increased the pressure gradient between these two areas and accelerated the winds over very known dust sources here. This is in summary how this works. So the high was here, paused here over the ocean for a few days, and accelerated the winds because of the steeper pressure gradient between these two. And this is all I wanted to tell you today. I would be happy to take questions. Thank you.
Thank you very much, Dr. Francis. I don't see questions on my screen. Andre, do you have any questions on your, have you received any questions?
And no, I haven't received yet.
We'll wait a minute. In the meantime, I will ask a question in the meantime. In your opinion, what is the most important research that needs to be done to improve our estimates of atmospheric dust in the MENA region?
So the difficulties or the challenge that we have for now is that some small-scale processes are causing massive dust storms. And we know that in climate models, or in the model that we have for now, in most cases, these are not accounted for because they are very difficult to do at small scale. So I think this is the most challenging aspect to represent accurately the dust activity over the MENA region. This is one side. The other point is regarding the impact on the radiation and interaction with clouds, because now we start to see that our knowledge on which we based our studies previously is not complete, and in some cases is turning to be the opposite. With this, I mean the impact of dust aerosols on the long wave, which now several studies have found that it's actually causing a warming effect, especially at night, instead of a cooling at the surface, as previously thought.
And so when you say small scale, do you small scale processes? Do you refer to the convective events, or the haboobs, or what? Yeah.
Yes. So convective events are very, very difficult to simulate pronostically in the models, but also, as I said, for example, the formation of low-level jet, even in the reanalysis with all the assimilation data we have, we still have difficulties to detect it. So for now, it's only on observations. We can do the detection of low-level jet and how much surface wind creates in the morning.
Thank you. Andrew, do we have any more questions?
No, no, Professor Marenko. We can move on to the next speaker.
Thank you so much.
Okay. Well, thank you very much, Dr. Francis. So we move on to the next speaker, which is Balint Alfogli from Slovenia, from Aerosol DOO, and who is gonna, oh, well, the title of the talk I have is slightly different. So I'll read the title that's on screen: Optical Absorption Properties of Mineral Dust Particles Generated by Storm Events in a Desert Environment. The floor is yours, Dr. Alfogli. Balint, I think I don't know if you're speaking, but I cannot hear you. I see your mouse moving. Maybe you're muted. Are you there? Andrew or Antonio, can you hear Dr. Alfogli?
Dr. Alfogli, can you unmute yourself because you are self-muted?
Yes, I cannot hear him either, but because he is indeed self-muted.
Now we can hear you.
It's working?
Yes,
okay.
now,
Okay.
Yes,
yes,
now it's working.
Super, thank you very much. Sorry for the delay. So I am talking about our extended application of our instrument, what is a atalometer, what was originally designed for black carbon and soot monitoring. But since also mineral dust has absorption, depending on the mineralogical composition, we can use this instrument for detecting mineral dust particles. This technique is already settled and already applied in our DNAP project with several participants, including also the Cyprus Institute. And the instruments are still running in Barcelona, Cyprus, and here Ljubljana. As an extension of this project, we moved 2 stations to Qatar to measuring dust particles, optical behavior directly in the source of the dust, means in the deserts. So what I'm talking about now is one case where when a heavy dust storm event happened, and this event provide us a good, let's say, condition to study the, let's say, the pure dust without any anthropogenic contribution, because we expected that during dust storm the aerosol particles mainly composed by the natural originated particles. So of course we have some problems with this technique, because the light absorbance of mineral dust is very low to compare to black carbon. So that's why we need to separate them, black carbon and the mineral dust particles. And also we need to concentrate the mineral dust particles to have enough absorption to measure. So for this, we can use the so-called virtual impactor technique. It's called virtual because there is no impaction in this device, but this instrument separates the particles based on the aerodynamic diameter. So this is how does it look like. We split the flow and we measuring the minor flow where the mineral particles are concentrated, while the major flow with the small particles, let's go away. So we need 2 instruments for this. One is working with the VI impactor, the other one is working with a PM1 fine cyclone inlet, because after the measurement, we have to correct the VI, the virtual impactor measurement by the PM1 measurement, because also the VI virtual impactor flow contains black carbon. What can, let's say, interfere the measurement due to the high absorption of black carbon particles. So that's why we have to make this correction. That's why we need these duplicates of the instruments. Okay, so regarding the study, so we have two locations, one in Doha, but the results what I am presenting was measured in the remote location. It is in the north of the country, close to Ras Laffan industrial complex, what can have some, let's say, contribution of black carbon particles. And here we are operating a VI PM1 attelometer system, as I described before, and also there is a PM10 filter sampling on every second day. So the storm, what happened, it is presented here. Maybe colleagues from Qatar are remembering that this happened in end of March or middle of March this year, and this drastic pressure drop, let's say, triggered this huge vortex what formed here, and this generated and transported the dust into the region, and this is how the city looked like those days. So it was a really severe event. And
2
this
minutes, please, Dr. Arfoldi, 2 minutes.
Okay, but what we measured, the orange is the coarse fraction measured by the virtual impactor, and the blue is the fine fraction measured by the PM1. If we zoom in and presented the PM1 in a separate axis, we can see that there are some peaks what are correlated, but other peaks, especially during the storm, are not correlated. So we have PM1 peaks here without coarse fraction peak, and here we have peaks in the coarse fraction without PM1. So what is this? What kind of aerosols caused these peaks? So for this we have to, let's say, study the spectral behavior of the absorption. Since our instrument is measuring the absorption at 7 wavelengths, we can also have information regarding a spectral behavior. So this is how the spectral behavior looked like during the this big storm peak. So you can see that at the short wavelengths we have a huge absorption comparing to the unique absorption what the black carbon particles follow. So compared to the black carbon particles, we have a huge absorption at short wavelengths caused by the mineral particles. And this different behavior or spectral behavior of mineral dust helps us to identify the mineral events. Also, these peaks, when we measure the PM1 peaks, shows the same character. So we have huge absorption at short wavelengths, what shows the mineral particle contribution. While during other events, we don't have the short wavelengths absorption. So it means that in both the coarse and in the fine fraction, we measure the black carbon particles because the absorption follows the typically black carbon pattern. So during this or using this spectral behavior, we can plot the short wavelengths angstrom exponent, and we can see that it's very sensitive for the mineral dust events. So we have these nice peaks in the angstrom exponent for short wavelengths during the storm episodes. So
please kindly wrap up. Please kindly wrap up. Thank you.
Okay, thank you. So this is the summary. Means that we were able to measure the absorption even in the PM1 fraction during the storm event, and the angstrom exponent for short wavelengths is a very sensitive indicator for dust storm events. So these are the main take-home messages of my talk. Thank you very much for your attention.
Thank you very much for this very interesting talk. Again, I'm looking on my screen and I don't see any questions, but I'll ask Andrew's assistance because I'm not sure. Oh, there is one here. What's the absorption angstrom exponent for the dust events? The question is from Dimitris Kaskoutis.
So during the dust storm event, the short wavelength angstrom exponent reached to 3. So let's say 3 times higher than it's expected for black carbon.
You say 2 to 3?
Yeah, until 3, yes.
Okay.
For the short wavelengths only. So for the whole spectra, it's lower, of course, but separately for the short wavelengths, it's reached to 3.
Okay. Any other questions?
Professor Marenko, I have assigned you one. Can you see it?
I see the one I just read from Dimitris Kaskoutis.
No, I don't know.
There is another one. I will say the last question. Could you please comment on the influence of dust on the use of AE33 as a PM2.5 black carbon monitor in this region without the use of any pre-concentration?
Yes, there is an impact also in the PM2.5 fraction, and I have a paper regarding this, so I can recommend to read this paper. It was issued this year, and no, I cannot tell you, but let's say it's up to 4% contribution. So let's say the measured black carbon, 4% of the measured black carbon can be mineral dust.
Okay, and one final question, and we move on to the next speaker. There was probably busy deposition in dust source regions during the Kuwait war with massive oil burning. Is there any evidence of that from your measurements?
No oil burning issued or emitted black carbon mostly. So with this spectral, let's say, separation, we can distinguish the black carbon from the mineral dust. So what I showed, it is coming from the mineral dust. Yes, and we saw the other peaks following the event where the coarse fraction and the fine fraction came from black carbon. It could be a source from oil wells, but we didn't. We cannot link it at the moment, so we didn't do any black trajectories calculations. But thank you for the point. We will check it.
Okay, thank you very much. Sorry that time is short, so I'll have to move on to the next speaker, who is Hossein Pana Ifa from the Institute of Advanced Studies in Basic Sciences in Iran. So, Hossein, the floor is yours. However, Hossein, I cannot hear you. I can see you, I can see your slides, but I cannot hear your voice. I think you're probably still muted, Hossein.
Dr. Panahifar, we can see clearly the presentation, but we cannot hear you. Perhaps if you try to unmute, please.
Professor Panaghivar is not muted. Maybe he could increase the volume. I don't know. Okay, I suggest we move on to the next speaker, and Professor Panaghivar tries to reconnect to join us again.
Yeah, I think that's a good option, Andre. Maybe I was wondering whether Professor Panaghivar has any option to call in instead of using the internet to speak, if it doesn't work. Anyhow, I'm going to move on to the. I'll let you solve this, and I will move on to the next speaker. Komzi Kenza, are you here?
Yes, I do. Hello, everyone. Do you hear me?
Yes, so Komzi Kenza is from Morocco, from the General Director of Meteorology, and the talk is about large-scale atmospheric patterns and PM10 pollution, the contribution of the Saharan Oscillation. The floor is yours.
Thank you so much. Hello, everyone. So I'm Kenza. I'm representing. I have an echo coming to my ears. Okay, let's try again. So I'm Kenza. I'm from Morocco, representing the National Weather Service here, and of course, I'm happy and pleased to share with you this work about large atmospheric patterns and PM10 pollution, the contribution of the Saharan Oscillation. And I want to first and foremost acknowledge the team members that helped to make that work feasible and whose names are appearing on the first slide. First and foremost, I want to share some context. So Morocco is the extreme northwestern African country. It is known by the diversity of topography within it, and it is under the influence of different effects, the Mediterranean Sea in the north, the Atlantic Ocean in the west, and the Saharan dust from the south. And this means that our country is under the continual interactions of low pressure areas and high pressure areas. And it is happening that we can see that type of phenomena invading the country. So you can see on the left this hotspot of ozone coming to the country from the west. And on the right, we can see this dust coming to the country from the west. And in fact, this means that our country is not only vulnerable to climate change, but also air pollution, and it needs to deal with what is emitted inside and what is coming from outside. So indeed, air pollution in Morocco is responsible for more than 13,000 deaths each year, which is about 7% of all deaths. It's the 8th main factor for global mortality in 2016, and more than 12,000 deaths are attributable to fine ambient particles. And this is exactly what we want to study. So we want to assess PM10 concentrations and characterize the relationship with large-scale atmospheric circulation in two regions from Morocco, Casablanca and Marrakesh. These two regions are different in terms of their positions or locations. So Casablanca is coastal, Marrakesh is from the inland, and also they are different in terms of the number of population and in terms of the economical activities within them. So to do so, we have used climate and weather data. I want to say that for climate, we mainly have used climate indexes. The North Atlantic Oscillation that characterize the interactions between the Azores High at the west of the country and the Iceland Low at the north of the Atlantic. And this is characterizing this flow that is coming to the west. Also, we have used the Mediterranean Oscillation that is characterizing the flow coming to the country from the north. And we have used air quality data, mainly average PM10, and also for selecting PM10 episodes or events, we have used the 95th percentile and percentile thresholding approach. We started by assessing correlations between PM10 and the different climate indexes, and we can see here that correlations are significant, meanwhile they are weak. So, and the Mediterranean Oscillation is better correlated with PM10. And then here we said, okay, let us see what is happening on the seasonal level. So here again, we can see that the Mediterranean oscillation is better correlated and that the correlation during the fall and the winter is moderate. Then here we said, let us take a step backward. And then we try to identify the different, to identify extreme PM10 events and see these events that are common to both regions, to Marrakesh and Casablanca, so that we can eliminate the probability of having a local PM10 event or a PM10 event coming from local emission. Then we found that we had 3 common events that appeared in fall, 2 in winter, 9 in spring, and 4 in summer. For all the events, we characterized them. We studied the different meteorological parameters related to them, and also we tried to redo or reproduce the sea level pressure so that we can see the flows on the surface. So in fall, we found that this pattern, where the country is under the influence of the ridge extending the high centered on Europe, is contributing to the creation of PM10 episodes. In winter, we found that the country is mainly under the influence from the stagnation of Siberian high, and this is creating kind of blockage of the air on the country and is fostering PM10 pollution. In spring, things start to shift, and now the country is under the influence of the Saharan trough from the south. In summer, things shifted completely, and the country is under the notable influence of the Saharan trough. So here it was clear that the country, when we have that the particle pollution in the country is coming from the flow from the south and the flow blocking in the north. And then we said, okay, so if the Mediterranean oscillation is explaining the flow coming from the north and this blocking, what can explain what is coming from the south? Then we created this index, which is the Saharan Oscillation Index, that explains this oscillation from the south. We draw this, and here you can see that it is a cyclical pattern. It is ranging between minus 0.2 and 0.2, and it is kind of having special character in winter and special character in summer. We calculated this index on the surface and also on the different atmospheric levels, and then we found that during summer there is a difference in the index between, for example, here the 200 HPA and the surface level. That means that this difference in the thermal centers can create a lift of the different of the dust in the south and create a different PM10 episodes. Also here, you can see the different correlations between the PM10 and the different climate indexes, and it is clear here this opposite behavior between the Mediterranean oscillation in the north, that is like a barrier, and the Saharan oscillation in the south that creates that flow that is coming from the south. So that flow is really blocked by the Mediterranean oscillation to create kind of PM10. Also, finally, I want to mention that this index is also found correlated to maximum temperature, mainly during summer. I came to the end, and thank you so much.
Thank you very much, Dr. Conti. So the floor is open for questions. Is there any? I see there is a question here. No, this is not. This is about the absorption of dust. It's probably not about this. Are there any questions? Andrew, do you have any questions on the?
We have no, Professor Marenko, we don't.
Okay, so I do have a question. So this correlation you found between the Saharan oscillation index and the PM10, is it valid for the PM10 measured in Morocco, or is it just for Morocco?
You are asking about observation. Is this from Morocco, right? You are asking about that?
Yeah. So yeah, exactly. The PM10.
Yeah.
Where's the PM10?
Yeah, the PM10 is what was measured in Marrakesh and Casablanca.
Oh, yes.
So
Okay. Okay.
these are observed measurements at the surface.
Yeah, it would be interesting to see if this oscillation index can be extended to other locations.
This is what we are working on, by the way. So we believe that this index can be correlated with the PM10 over the south of Europe, mainly Madrid and Barcelona, and we are working on that now. Yeah.
Okay, thank you. Are there more questions, Andrea? Do you have any?
Yes. PM10 increased with these oscillations?
So yes, so we just to understand, the oscillation can explain the flow that is coming from the south, and exactly when we have that flow coming from the south is fosters PM10. So we cannot say that it increased with the oscillation, but it can be explained by the oscillation, and it can increase by the flow, because mainly the oscillation is explaining how the two centers of pressure interact together.
Okay, and one final one. The SOI appears to be annually varying. Does this justify to call it an index?
Can you say it again?
The SOI, I don't understand what it says, appears to be annually varying. Does this justify to call it an index?
Appears to be, I didn't get the appears to be what?
So basically, the new oscillation index has an annual variation. It has a seasonal variation. So the question is this a good reason to call it an index?
Yeah, so the good reason to call it an index is the fact that it is measuring the anomalies between two centers. So this seasonal or cyclical pattern is explaining how these pressures, the centers of pressures, are interacting together. And calling it an index is about to see to what extent one center of pressure is stronger than the other center of pressure.
Okay, thank you. I think we should have another. No, I think we've overrun, haven't we? So we don't have time for more questions.
We are past the 3 minutes for Q&A for Professor Genza Komsi. So I would urge that we proceed with, we go back actually to Professor Panahifar. If the
so thank you very much. Thank you very much for this talk. And yes, we go back to the previous talk, which we didn't have, from Hossein Panahifar from Iran, on vertically resolved optical and physical characterization of aerosol layers of Amman, employing Calypso satellite data. The floor is
Thank you. I hope you can hear my voice right now.
I can hear your voice, I can see you, and I can see your slides.
Okay, great. Good afternoon, everybody, and sorry for technical inconvenience. I want to present some part of our result to monitoring vertical result optical and physical characteristic of aerosol layer over Amman and Jordan using ground-based and satellite data. And I want to appreciate my co-author Tariq Hossein from University of Jordan to provide ground-based measurement for me. As an introduction, I want to say that the Eastern Mediterranean region is located in the middle of the global dust boat, and Jordan is situated in the cross of Eastern Mediterranean and southwestern Asia. The land of Jordan is located in the south of Syria, west of Iraq, northwestern Saudi Arabia, and east of Israel. So the region are highly polluted with different aerosol type of natural and anthropogenic sources from Europe, from Africa, and also from Asia. Quite lots of research have done to monitor and measure the atmospheric air pollution by use of ground-based particulate matter measurement, particularly in Israel and Amman. However, the knowledge of vertical structure of the atmospheric aerosol is still insufficient in this region. So this is the aim of our study, to raise awareness about the spatiotemporal distribution of aerosol optical and physical properties in the Eastern Mediterranean region. And to do this, the use of the ground-based measurement campaigns conducted from May 2018 to March 2019, and my colleague Tariq performed all of ground-based measurement by use of two high-volume sampler installed in the University of Amman in Jordan. regarding the satellite data, we mainly use of the recording of the space-borne LiDAR Calliope and also from the measurement of the MODIS. And as a typical example of the result which we can use from the Calypso recording is the attenuated backscatter coefficient at 532 nanometer, which you can see that it reveals the vertical structure of the aerosol in the atmosphere. We also can use of the Calypso recording to determine the bottom and top of the aerosol layer, differentiate cloud and aerosol, and use of the depolarization ratio measurement of the Calypso to classify aerosol time. In addition to the ground-based and satellite data, we use of the two-step polyphony method, which introduced by Elizabeth Memory and Ansman in a series of papers, and applied these techniques to measurement of the Calliope. And by using of this technique, we can retrieve high threshold particle backscatter and extinction coefficient and vertical structure of the mass concentration of the atmosphere in the region of the interested studies. As an example of a dust cases, I want to explain with more detail about the dust storm which happened on the 7th of June 2018. This figure shows the ground-based measurement measured on the Amman, capital of Jordan. And this plot illustrates that a gusty wind with a speed with more than 10 meters per second reach to the Amman city and bring dust plume to the city. And by the arrival of the dust storm, the PM concentration increased to around 120 microgram per cubic meter, and concurrently the horizontal visibility decreased to lower than 4 kilometers and relative humidity also decreased. All of this evidence confirmed that the dust storm happened within the city. And also the aerosol optical depth from deep blue, MODIS deep blue, and the aerosol angstrom exponent confirmed the existence of coarse dust particles on the 7th of June 2018 over the Amman, which caused the increase of the aerosol optical depth and decrease of the angstrom exponent over the Amman. This plot shows, the red line shows the ground track of Calypso, which pass from neighboring area around the Amman, which is indicated by the green circle. And this is the attenuated backscatter coefficient, cross section of attenuated backscatter coefficient recorded by Calypso on 7 June of 2018, and this result showed the existence of a dust plume which extended from the surface up to 3.5 kilometers. And if we average this LiDAR recording and apply the polyphony method on it, we can retrieve a vertical profile of the particle backscatter coefficient, and we also can retrieve the particle depolarization ratio. And these results reveal the existence of a two-layer structure in the atmosphere. The lower layer from the surface up to 1.5 kilometers contain the particles with depolarization around 12-13, and the upper layer contain particles with depolarization around 0.4. And if we use of these
2 minutes, please, Professor, 2 minutes.
Yeah, if we apply all of these measurement to the total particle backscatter coefficient, we can decompose the total particle depolarization backscatter coefficient to the contribution of the dust, of fine dust, and pollution, and pure dust. And the most important result at this slide is here that we can conclude that at the lower part of the atmosphere, it contains with the mixture of the fine dust and pollution, and the upper layer of the atmosphere contain of the pure dust particles. And we also use of the high-speed backward trajectory to determine the source of these particles, pollution from local sources, and dust particles originated from somewhere in the border of Iraq and Saudi Arabia from the previous day. And as a conclusion, we evaluated Calypso profile for all of the measurement period over the Jordan, and this result shows that the top height of the aerosol layer observed and detected over the Amman is from 0.5 to 2.5 kilometers, and mass majority of the aerosol type is polluted dust, and after that dust and pollution. And so we use of the Calypso recording to see the monthly variation of the aerosol and classify the aerosol type based on the depolarization ratio, which I skipped this slide. And this brings me to the summary. The vertical profile of the aerosol layer investigated over Amman by use of the Calypso, and the highest frequency of occurrence for top height of lofted layer contain polluted dust observed from 0.5 to 2.5 kilometers, and the dust aerosol influence Amman from March to June, and the polluted dust and pollution particles with the low depolarization ratio impacted the atmosphere of Amman from October to February. Thank you very much for your attention.
Thank you very much. It was very interesting talk. Again, I don't think I have questions on my screen, but I ask Henry's help there.
No, not yet.
Okay, so I will ask the question in the meantime, waiting for the questions. Are you still there?
Yes, yes. Yeah.
Yeah, okay, because I cannot see you anymore. Would it be easy to extend this study? You studied the Amman, location of Amman with the Calypso, but I suppose, how easy would it be to extend it to a wider region?
Yes, it's a very good question. I mentioned to the Amman because we use of the ground-based measurement performed over there. But when we use of the Calypso recording, we can extend to the whole region of the Jordan, you know?
Yeah, it would be interesting to have it for the whole EMA region, really.
Yeah.
That made it too much, but anyhow. Any questions?
We don't have any question.
Last call for questions. Okay, if there are no questions, I think we can end the session on dust. Thank you very much, Pier Antonio and Andri, and I'll leave the floor back to you for the next session.
Yes, thank you very much, Professor Marenko. I would like to thank you, of course, for chairing the session, and all the participants, the invited speaker, and our oral presenters. Just for the sake of giving the people who are interested directly in the climate modeling and prediction session, there might be people who will join in at exactly 3. So I will give a 5-minute break to allow for any people who have not joined us until now to join exactly on the predetermined time. But I'm happy to say that we are 5 minutes ahead of schedule. So I will spare you with trying to fill in 5 minutes with my babbling, and I will invite you all back at 3 o'clock Cyprus time for the climate modeling and prediction session. So, dear colleagues, again, good afternoon, good morning, or good evening, depending on the time zone from which you are following us. Welcoming those who have just joined and welcoming back those who have been following us since earlier. We are now going to proceed to the climate modeling and prediction session. This session will be chaired by Associate Professor Panos Hadjinikolaou from the Climate and Atmosphere Research Center of Excellence. Just a quick introduction for those who have just joined. In this session, we will have one invited speaker who will present for 15 minutes, and we will have a follow-up Q&A session of 5 minutes. I will personally remind that 5 minutes the speaker, and then 2 minutes, and then the chair will invite to wrap up if we go beyond that. And then we also have the pleasure to welcome also 3 oral presentations. Professor Hadjinikolaou, I remind you that the oral presentations are of 7-minute duration each, followed by a 3-minute Q&A session. For the oral presentations, I will make a reminder only once at the 2-minute mark. So, without further ado, climate modeling and prediction session chaired by Associate Professor Panos Hadjinikolaou. Professor Hadjinikolaou, please, the virtual podium is yours.
Thank you, Perantonios. So this session, it's a diverse session, but mainly focusing on results for model simulations or serving model simulations, because later on we have also the virtual poster presentations. Regarding the talks, again, we have a diverse, let's say, portfolio of 4 talks, including actually 2 internationally renowned atmospheric and climate scientists. And I will start by introducing our invited speaker, who is Professor Georgi Stenchikov, who I have the pleasure to read his papers in the 1990s on nuclear winter and volcanic effects on stratosphere. But now I will invite him to talk about the impact of global warming on regional climate over the Arenpia Peninsula.
Thank you, Panos. Open system preferences. So I would like to share my screen. Could you see my screen?
Not yet.
Okay. So 1 second.
In the meantime, I kindly remind all the participants and I urge them to use social media and to post following our hashtag, which is hashtag EMME4 with the number 4 climate. So hashtag EMME4 climate. We will be very happy to see a lot of posts and likes and tweets and retweets populating this hashtag. Thank you, Professor Hadjinikolaou. Over back to you.
So what should I do to share the screen? I see the button. See your screen, click to start sharing. And it gives me open system preferences, some go to webinar, capture this.
Are you joining from the application or from the browser?
From application.
I assume that Professor Stenchikov has given the panelist privileges.
I have made Professor Stenchikov a presenter, so he must be able to share his screen.
So what should I do to share the screen?
There is a share button.
Yeah, I did. And go to meeting.
As to the simple attendees, it says waiting to view Georgi Stenchikov's screen. We have this notification on our screen. Maybe it's trying to connect or something.
So what is now?
Maybe the previous speaker, or we're still sharing the previous screen. Can we confirm?
No.
I see.
Professor Stenchikov, can you send me your presentation and I will share it?
Sure.
Okay, Professor Hadjinikolaou, if I may suggest, can we move on to Dr. Doumos' oral presentation and give some time for the technicality? Yes. Perhaps even Professor Stenchikov can log out and log back again. And in the meantime, also gain some time for Professor Stenchikov to send to us, to Andrei Haralambous, the presentation, so we can at least change slides, but so we don't have a dead time live. So if Dr. Doumos is ready to pick up, then let's go for that. And I leave the chairing back to you, Professor Hadjinikolaou.
Okay, so the next talk, let's move on to the presentation by Athanasios Doumos, who is a PhD candidate at the Climate and Atmosphere Research Center here at the Cyprus Institute. Thanos, are you following us?
Yes. Hello. Can you see my screen?
Yes, and we can hear you.
Okay. So I will.
Only a bit louder, Thano, if possible.
Yes, of course. Okay.
Great. Thank you. Thank you very much.
Okay. So, hello everyone, my name is Athanasios Doumos and I'm a PhD student at the KRC. So this presentation will be about the sensitivity analysis of a WRF model PBL schemes in simulating temperature extremes over the Middle East, North Africa region. So correct representation of the boundary layer is critical to achieve realistic regional climate simulations, especially regarding the surface variables. So in this study, the main objectives will be, first of all, to examine the sensitivity of the performance of the WRF model to the use of three different PBL schemes. Also explore the differences of the WRF simulated temperature and extremes resulting from the choice of PBL schemes. And also reveal the most suitable scheme for the Middle East, North Africa domain. So now we'll describe the model configurations. So we perform some runs with the WRF version 4.1 in 24 kilometers horizontal resolution at the 35 vertical levels. So the model domain is the MENA cortex domain, and runs were performed for an 11-year period from 2000 to 2010. and the boundary data were taken from the ERA interim reanalysis. So at this schematic, you can see the physics of the WRF model and their interactions. At the small boxes, you can see the set of the physics parametrizations that we use in our runs. And as I said before, the study focuses on the PBL schemes, so we use 3 different PBL schemes. So now we'll present the main results, starting from the summer maximum temperature. So first of all, let me describe further pictures. On the top left, there is the ERA 5 climatological average, and the other maps shows the model biases from the ERA 5 for the 3 schemes. So model biases strongly vary according to the geographic location. The ASM2 scheme seems to be warmer than the MYJ and YSU, especially in parts of North Africa where we observed opposite signs, biases. The MYJ shows strong biases in some areas, both cold and hot. And overall, we can say that YSU scheme shows better performance. Now for the summer minimum, again, we see different biases, different magnitudes and signs according to the geographical location. This time we see more cold biases in many areas. The ASM2 shows the strongest cold biases, especially in North Africa and Arabian Peninsula. And again, YSU seems to perform relatively better. Also, it will be interesting to investigate the summer surface specific humidity, where we see some notable difference among the 3 schemes. So the ASM2 is the driest scheme, and the MYJ is the wettest and overestimates moisture in many parts of the MENA, especially in the North Africa. So we have significant differences among the 3 schemes, especially in the Northern Africa, and these differences can be linked with the differences that we saw before in the maximum temperature. So MYJ predicts lower temperature and more moisture, and this is possible due to weaker vertical mixings. And YSU seems to have the smaller biases from ERA 5. So now regarding the heat extremes, about the TXX index, which is the warmest day of the year. In this case, the WRF overestimates the index in the most areas of the MENA. ASM2 seems to be the warmest, with warm biases in most areas, especially in the Mediterranean region, where the other 2 schemes show also colder biases. The MYJ shows substantial warm biases in parts of Egypt and the Middle East. And regarding the warmest night of the year, and this time the WRF simulations produce cold biases in many areas, in contrast with TXX. We can say that the model biases are very dependent on the geographical location.
2 minutes, Thanos, please. 2 minutes.
So regarding the ASM2 and MYJ, these 2 schemes show significant cold biases on some areas, and the YSU seems to be a bit warmer, less significant cold biases, and on average, you can say it has weaker biases. So concluding, the model biases are dependent on the geographical location at the time of the day. On average, WRF simulations tend to overestimate maximum temperatures and the TXX index, and on the other hand, underestimate the minimum temperatures and TNX index in many parts of the region. Overall, we can identify the YSU scheme as the scheme with the least bias. So the MYJ scheme overestimates moisture, and on the other hand, ASM2 is the scheme which is the driest and usually the warmest, especially regarding to the daytime PBL. So-called moist planetary boundary layers can be caused by the underestimation of vertical mixings and so the entrainment. But further research should be conducted to confirm the above conclusion. We can include in our analysis, analyze the vertical profiles, estimate the boundary layer height, and account for fluxes. And with that way, we can reveal the physical causes of model biases. So at this, now I would like to thank all of you for your attention.
Thank you very much, Thanos, for the presentation. Do we have any questions from the audience? I don't hear or see any question typed. Can I ask
Professor Hadjinikolaou?
Okay.
Me neither. So unless you have a question yourself to Thanos, to Athanasios Doumos.
Just a very brief comment. So although one of the two schemes that is notably different from the other two shows the difference in the main variables, Tmax and Tmin, it doesn't show so much difference in the extreme index of the temperature. So this is also something worth investigating.
Yeah, sure. Yes.
Okay, thank you very much, Thanos.
Nicolau, I have assigned you one question. Have you seen it?
In the chat, no. How can I?
You must see a question section now.
Okay, yes, I think I can see it, but there is a very small window. So can you please read it? I can see only half line. Sorry.
Okay. Could an absorbing aerosols play a significant feedback on warm extremes in MENA?
The question is if investigate the aerosol impact or if they could affect.
I think both.
If they could absorb.
Absorb what? Can you repeat the question?
Aerosols.
Aerosols can absorb.
So the question is if the absorbing aerosols could play a significant role through feedbacks on the warm extremes on MENA.
Yes, I haven't investigated, but in general, we see some warm biases in maximum temperatures and cold biases in minimum temperatures. So that can be an effect of radiation and the interactions with aerosols. So yes, it could play a role, and it's a good idea maybe to further investigate that. Yes.
Okay. Although I assume the role of the aerosols in the model is quite minimal. I mean, they're just from some lookup tables, but I think we agree there might be an important role there. Yes. Thank you for the question also. So how should we go about now in our schedule with the next talk?
Well, my question is if Andriy, have you received the presentation from Professor Stenchikov? I think you might need some sort of confirmation.
I did, but I need some time to download it. So I suggest we move on to Anna Gerkali.
Anna Gerkali then, okay. And then we will have Dr. Alpert from Tel Aviv.
He's still not with us.
Okay, so let's go to Anna Gerkali. Professor Hadjinikolaou, over to you to chair Anna's presentation, which is an oral presentation. So 7 minutes, please, and then 3 minutes of Q&A. The floor is yours.
Okay, Anna is a research assistant at the Climate and Atmosphere Research Center at the Cyprus Institute, and she will talk to us about her experience with weather station satellite and population datasets and how this can help us understand better the urban heat island in the region. I cannot hear Anna.
We cannot hear you. Yeah.
Can you hear me now?
Yes. Please go ahead. We can see your presentation well and hear you.
Great. Hello, my name is Anna Dirkalin, and in today's presentation, I will present you my work entitled Utilizing Weather Station, Satellite and Population Datasets to Estimate Urban Heat Island over locations in the Middle East and North Africa region. Firstly, local weather and climate conditions are affected by the presence of cities through their perturbation on the surface energy balance. A well-known effect is urban heat island, where land surface and near surface air temperature are higher over a city compared to its rural surroundings. In order to determine and project this local warming additional to the large-scale global warming, observation-based urban heat island estimates are necessary for the evaluation of high-resolution urban resolving climate model simulations. The main research objectives of this work is to combine air temperature station records with urbanization data derived from land and population data, and also to examine and provide credible urban and rural temperature differences for the MENA region. For this work, we are using an observation dataset. Basically, it's becoming from the integrated surface dataset, and more specific, the global summary of the day, which contains raw daily weather elements like daily, maximum and minimum temperature, wind speed, precipitation, and other elements. In general, there are more than 10,000 stations globally, including the MENA region. And for these observations, quality control and analysis was performed. Like multiple years of data were analyzed to ensure the continuity. For this study, we are using 2000 until 2010 year period. Only valid stations were selected, and the mean values for each station were calculated based on the 5-3 rule from WMO technical report. For land cover data and population data, we are using the global human settlement layer. This method, as you can see from the picture, was designed to combine information from population sensors with built-up data and to downscale population into a grid of 1 kilometer resolution according to the presence or absence of build-up in the grid. The new layer represents 7 classes characterizations for each grid based on the population of inhabitants per square kilometer and the built-up surface share on permanent land. As you can see here, the last image is the proposed layer. An overview of the distribution of the stations. Here you can see there are 640 valid daily stations for the MENA region. For the period 2000 until 2010. If we are looking closer, you can identify there the 7 classes that global human settlement provides. Also here, you can see the 4 time steps that the global human settlement layer provides for 4 different years. And through the years, cities are fast growing. And as you can see, the class of each grid changes rapidly. Layer of the 2000 year was selected for the following analysis based on the validity of the observation data. And here you can see an example of urban-rural pair of station in Jordan, in Amman. Some preliminary results for the whole region. We identify 120 pairs of urban-rural meteorological stations based on some criteria. So the distance between the stations must be less than 100 kilometers in country level. Also, monthly mean followed the 5-day rule, which means months with more than 5 missing days or 3 consecutive missing days are results to an A month. So here in the histogram, you can see the summer climatological values for which is the average of 11 years monthly data. And there are more than 70 pairs of stations that have a positive urban heat island. We do the same procedure for maximum and minimum temperature. So you can see we have positive urban heat island for the nighttime values, and in contrast with the maximum, which we have negative urban heat island for the daytime values. And last, here you can see an example of a pair of urban and rural station. We calculate urban heat island as the daily urban minus the daily rural. We corrected these temperatures with the lapse rate correction. And in the map, you can see that we have an urban station in Alia, which is included in the red boxes, and a rural station in Marca, whereas these two stations they have approximately 27 kilometers distance between. And on the graph on the right, you can see that through the year, they have positive urban heat island.
2 minutes, Anna, please. 2 minutes.
Yeah. And to conclude, a combination of a global human settlement layer and temperature observations from ISD stations was performed. About 70% of the pairs selected have positive urban heat island from the summer monthly average. And for the year 2000, throughout the year, the urban heat island, the daily values are more than are positive. For future work, in order to evaluate the model, we have to consider other meteorological elements like wind speed and geomorphological details of the region. Same procedure with extended time periods, and we have to include hourly period calculations for diurnal cycle. Last but not least, we want to finalize credible urban heat island pairs for regional climate model evaluation. Thank you for your attention.
Thank you very much, Anna. Let's wait for a few seconds. If some questions appear, I found now the panel. Where are the questions? I don't see any new question, unless I have to delete the old one.
No, there are no questions so far.
Okay, while we're waiting only for a few seconds, can I ask, Anna, you mentioned in your further work the wind speed.
Yes.
So what we have shown us now about some preliminary results over these pairs of stations that you selected, have you used the wind speed criteria?
Actually, not yet, because by now we wanted to find credible urban heat island pairs and then to further investigate the wind speed. Is the next step.
Yeah, I think, yes, it sounds like it should be the next step, because otherwise a strong wind will flatten out any temperature difference between urban and rural. So yeah, it's good that you are about to do that too. There is a question actually. Let me also undock it so I can see who is asking. Okay, actually, sorry, we have two questions. What is the criteria for rural versus urban by Amnajrar?
So urban station, we have a grid in 1 kilometer resolution where the grid is equal to 30, the index is 30. It means that population and built up is higher than a number. So I have here exactly the numbers of how do they, from human settlement layer, how they define urban and rural. So the red here is, so you have to have population density more than 105,000 people per square kilometer and to be more than 50% built up the area.
Okay, I stop you here. It's pretty evident from this table. There is some criteria for this, and they come up to some classes. Okay, we have more questions from Christos Foundoukis. Have you looked at extreme rainfall differences because of the urban heat island difference between the stations?
About rainfall?
Yes. Have you looked at any rainfall, extreme rainfall differences?
No, we focus on temperature first. We wanted to see what
Okay,
is going
that
on
is
with
a good
temperature.
idea at some point to examine. So we have two quick questions by Jos Lelyveld. Does the type of build-up area play a role?
Yes, because it sums up how much built-up area is in the grid. So it's a combination of population and build-up.
Okay, but this is the how much. Jos is asking about the type, the nature maybe of the built-up area. And perhaps maybe they account for high rise and low rise. That's the only distinction they do. Is that correct? Or not even?
I think.
So it is mainly on the dense of the urban area, and I think not of the type, but we should look at that too. And the last question, for example, related to population density, that was the follow-up of the question. Well, population density, you just show that it is taken into account together with the built-up area. So
yes, it's a combination of these two factors.
Wrap up the Q&A, please.
We finished the Q&A. Thank you for the questions and Anna for your presentation.
I'm ready for my talk. It's Pinchas Alpert.
So we proceed with Pinchas.
I have to share my screen. It's
so next is Pinchas. Control Center, advice, please.
Can you hear me? Hi, Panos.
Yes, we can hear you well, Professor Alpert. Of course, there's a technicality with the name you are showcasing. It's not, of course, Andri Haralambous, but you should be able to share your screen and to continue, and we will have the invited speech of Professor Stenchikov closing the session. So please, Professor Alpert, we see your screen now. If you can pull up your presentation, your slides.
Do you see my presentation?
Yeah, we see a screen. Your screen, I think.
You see my screen?
Your desktop, yes.
Okay, so I can talk. Thank you.
I can see the desktop, not the presentation yet. Maybe there is a lag. You have to
Can
launch
you
it.
open your PowerPoint presentation, Professor Alpert?
Yes, I sent it to Andri because I didn't find the share button.
Okay, then you don't have to share your screen then. It has. Look, but you can
have managed to share your screen now. You have managed to share your screen, so just go to your presentation and play it on full screen mode.
Okay, now you see it?
Yes, we see it. Yes.
Excellent.
Please go ahead.
Okay.
Yes.
The title of my talk.
Sorry, Pinchas, sorry, 1 second. Can you go to display settings on top and choose the kind of a full screen? I think we've had this before in one previous session, because now we can see also your next slide. Yes.
Okay, so let me see how I do that. No, now you see everything.
In the upper side of the screen, there is a show taskbar, display settings, and end side show options, 3 of them. The middle one is called display settings. Not where you are now, just go further up, above the dark rectangle now. Just go further up in your screen. Exactly there.
Display
Click
setting.
on it. There you go. That one.
That one. Okay. Now you see the screen.
Thank you very much.
Thank you. Okay. The title of my talk is an unknown maximum lag correlation between rainfall and aerosols at 140 to 160 minutes, which is about 2.5 hours. Let me explain what we did. This is an example of the time series of rainfall and aerosol for a specific event. On the left side, you can see the rainfall in millimeters per half an hour, which is the blue line is the rain. And you can see also the dust with an opposite coordinate, so that it will fit the rainfall. The coordinate for the dust shows it's increasing downward. Now you can see both the rain and aerosols for a specific event on February 2015 in Israel station, Modi'in. Now you can see the peak of rainfall. At this, you can see but what I show you here. Now, after about 2 hours, you can see the minimum in the aerosols, which is now a maximum because it's the opposite direction. You understand what I mean? The correlation between two cases, and you can see more cases, rainfall followed by a reduction in aerosols. Here, you can see it also in other cases. The correlation in this case is found to be the highest, -0.5, at 120 minutes lag, because there is a lag between the rainfall and the scavenging and the removal of the aerosols. What we did, we looked into near surface aerosol rainfall correlations on time scale from minutes to days and weeks. Many experiments and different resolution, time resolution of daily, of 60 minutes, 30 minutes, 10 minutes, 10 stations in Israel and California, which is also a Mediterranean climate. The key challenge was to find stations having that monitor both rainfall and aerosols with enough temporal resolution. Now you can see the stations, about 8 stations in Israel and 2 stations in California, which is also a Mediterranean climate. This was published in GRL with the title of the talk, An Unknown Maximum Lag Correlation Between Rainfall and Aerosols. We were very surprised to see that this type of correlation, which is significant, is not found in the literature. Here are many events and many stations. In this case, you can see at 60 minutes time resolution, you can see a lag correlation of 120 minutes about. By the way, the black line is the average of all the events that we looked on this specific event. No, there are several events here, but several stations. And the line of significance, statistical significance, is given by the dashed line. So zero correlation is here, and the zero lag line is here. And you can see that about 2 hours after the rainfall, we have a significant lag correlation between rainfall and aerosols. How to explain such a significant correlation between rainfall and aerosols? Perhaps the scavenging is the washout of aerosols by rainfall, perhaps is the strongest one. Here you can see the lag correlation which exists for California stations, California average, and for the Israeli 60 minutes and 10 minutes average, they all show a significant correlation at this time of following about 2 hours after the rainfall.
2 minutes, please, Professor. 2 minutes.
Now, the key points. I mentioned the highest negative correlation were consistently at a positive lag of about 2 hours. Probably this is the result of the scavenging, washout of the aerosols depending on the rain, but also on other processes like aerosol sources, hygroscopic growth, and transport. There is a consistent lack of significant correlation at negative lags, which is very interesting. You can see here on several days, 10 days, that we can see the minima at the 1 day, and then gradually the correlation returns back to near zero or near normal. So the key points I already said. I will perhaps mention that we are now studying in models, in climatic models. This is jointly with Drew Schindel, and you can see here the observations, which we see the strong negative correlation, but in the model we don't see it, but we do see similar structures of maxima. I will leave time for a question or two. Thank you. Hello?
Thank you very much, Professor Albert. Thank you very much.
Thank you.
Let's see if we have any questions from the audience first. And apologize for not answering your email before about how to share your screen. Sorry, I wasn't.
We don't have any questions.
Okay, so
there is actually a question that popped up in the organizers and panelists.
Okay,
so
I can read
it. You can see it. It's from Professor Marenko. Please, Professor Nicolaou.
Okay, Professor Marenko says, very interesting to see this correlation between rainfall and aerosols, which seems to indicate the effect of scavenging. Why do we expect a time lag between the two?
Why do I expect this time of 2 hours? This is a very interesting question that it is probably a combination of several processes that act together, like bioaerosols growth, which follows rainfall. But the scavenging is the strongest effect. But what is perhaps the key message from here is that climate models need to see this most statistically significant correlation between aerosols and rainfall. We do not have any similar correlation that is so significant over so many events, rainfall events, and so many stations. This is my main key point or message from this study.
We have another question by Francois Dulac, who also asked a previous question about the aerosols in the previous talk. So the question is, do you find the same type of lag correlation with PM maxima back after rainfall?
It is including, you mean PM1, not PM10. Yes, we did calculate for several events with PM 2.5. We didn't have the data for PM1. Francois, I will be glad if you have the data from the same location to go and look in this because it is an interesting point, but the differences between PM10 and PM2.5 were small, and they are discussed in the GRL paper.
Okay. Do you have time for another question?
No, Professor Nicola. We actually have to move on.
Okay.
Thank you.
Professor Albert, thank you very much.
Thank you a lot.
And I want to mention here that I'm honored by your presence in this session, because you and also our next speaker, you are a renowned atmospheric and climate scientist with hundreds of publications and thousands of citations. So now let's move on from where we started for the invited talk by Professor Georgi Stenchikov. We can see the presentation.
Okay.
Yes.
Okay, thank you. Okay. Thank you very much, and sorry for delay. Somehow not entire screen is on the. Okay. Let me remove my. Okay, it's not better. Okay, so my name is Georgi Stenchikov. I'm from KAUST, and I represent Division of Physical Sciences and Engineering and Earth Sciences and Engineering program. My research is about regional climate change, climate feedbacks, dust effect on climate and air quality. This is my group efforts, and I will talk on behalf of my group. The pace of warming in the Middle East is higher than average over the globe. We see this from observations for the past and from model runs for the future. The regional climate is more challenging to predict than global because of the non-linear effect of circulation and desired high spatial resolution. New high-resolution predictive methods are required to produce a reliable regional climate forecast suitable for planning and adaptation purposes. In this talk, we evaluate the mechanism of regional climate sensitivity in the Middle East. For this, we consider the observed regional impact of the 1991 Pinatubo eruption on Middle East and quantify the impact of regional dust aerosol forcing. I also introduce the new modeling tool that we developed for these purposes, and so partly want to advertise this tool for regional climate studies applications. Next slide, please. We considered 21 CMIP5 models to study the changes over Arabian Peninsula and globally. Here on the slide, you see RCP 4.5 and RCP 8.5 business as usual scenarios. So the anomalies are calculated with respect to pre-industrial, and red shows global anomaly and pink shows Arabian Peninsula. And you see that pace of warming over Arabian Peninsula is much higher, at least 30% higher on this slide with respect to global. And this, this difference in pace depends on reference period. If you will take reference period in 20th century, so the difference will be even higher. If you look, please, next slide. If you look at a special distribution of global of warming, we see that central part of Arabian Peninsula warms much faster than coastal areas. It indicates the important role of regional seas, the Red Sea, Arabian Gulf, and Mediterranean. These seas are not well, especially Red Sea and Arabian Gulf, not well approximated in the global model because they are small and resolution is not enough in global models. Next slide. If you talk about Middle East climate, so we have to account for effect of dust. Middle East contributes about 20–30% to global dust emission, and dust affects the regional radiation budgets, regional seas, and produce huge radiative forcing over the Red Sea, probably the largest in the world for solar radiation at 60 watt per meter squared. We have to mention also that dust fertilizes, provides nutrients to marine microorganisms, both in Red Sea and Arabian Gulf. Next slide. Next slide, please. Previous one. Please, previous one. Yes. Could you make full screen? In this talk, to demonstrate the effect, the regional climate sensitivity, we consider two studies. The first one is the effect of Pinatubo on Pinatubo eruption of 1991 on the Middle East. Pinatubo produced a huge volcanic cloud that reflected solar radiation and cooled the planet by ½ degree. But the effect on Middle East was at least 3 times stronger. And the snowfall in Israel and Jordan in winter 1991-1992 was really extreme event that was remembered for a long time. And the second case study I will present is effect of dust on Red Sea. So left up, you see the slide of trend of optical depths of dust over the area, and you see that over Arabian Peninsula and Arabian Sea, trend is especially large during recent 15 years. And if you look at spatial distribution, we see that optical depth over Red Sea in summer, climatologically, is higher than over major Rub' al Khali Desert. This is because dust is transported by prevailing northern wind along the Red Sea, and is trapped by high range of mountains along the coast of Red Sea, so in the southern part. And this 2-kilometer layer of dust has optical depths about 1 and huge radiative forcing. This forcing was never so accounted for in the effect of on the Red Sea, and we tried to do it in our work. Next slide, please. Could you? Okay. To study this, we coupled WRF model, regional atmospheric model, with regional ocean modeling system ROMS. We provided effect of volcanic and dust aerosols into the model and conduct calculations for atmosphere in larger domain with 30-kilometer resolution and in the internal domain with 10-kilometer resolution. And internal domain, atmospheric domain, is coupled with Red Sea simulations with 2-kilometer resolution. This work is published in Osipov and Skenchikov and Journal of Geophysical Research in 2017 and 18. This was dissertation work of Sergei Osipov. He gave a talk today in the morning on atmospheric chemistry, but he also worked on regional climate modeling. And it is, I would say, interesting model. It is first attempt to use coupled regional model to study climate change in this region. Next slide, please. So why it is so interesting to look at Pinatubo eruption? So as I said, Pinatubo cooled the planet by ½ degree, but the effect in Middle East was at least 2-3 times larger. Here you see the anomaly of SST over Red Sea, and the decrease of temperature is about 1 degree after Pinatubo eruption. It is 3 times higher than average over globe that was about 0.3 degrees. Jenin et al. Showed that corals were bleached after Pinatubo eruption in Aqaba Bay for Aqaba Gulf, so at least for 2-3 years. The model below, you see the model simulation that we can compare with observations, and model reproduces this cooling extremely well. Next slide. If you look at temperature, surface temperature response, in the first row, you see total temperature responses as model calculated, and from era interim reanalysis, anomalies are calculated with respect to climatology. And we see that the model produces pretty reasonable results that compared well with observations. But model also allows us to study the separate effect of direct radiative cooling and effect of change of circulation. We call it dynamics effect. And you see that direct radiative cooling from a huge Pinatubo eruption is about 3 times smaller than effect of change of circulation. And this indicates once more to the complexity of the climate in the Middle East. This dynamic effect is associated with the positive phase of Arctic oscillation that affected position of subtropical jet and allowed cold fronts from the north penetrate further to south. This is important feature of this area, and this dynamic control so is difficult to reproduce in the models. Next slide. Surface air temperature was not the only that was affected by Pinatubo eruption. Red Sea was severely affected as well. Red Sea is an evaporation basin. Internal sea, so the water is coming from narrow Bab el-Mandeb Strait and so moves to the north. You see on the left up the temperature in the climatological temperature in the Red Sea. This water at the top of the sea cools when it is transported to north, and cold water in the north sinks, producing so weak overtoning circulation in the right column up. So the vertical stratification in the Red Sea is very low. Only in the northern part, it is only few degrees between bottom and top, and so that's why so this mixing is very sensitive to the temperature at the upper layer of the ocean. Cooling caused by volcanic aerosol intensifies mixing and so make overtoning circulation 50 times stronger than in climatological mean case. In comparison with global case, so this is about 5 times stronger, because Pinatubo caused increase of overtoning in Atlantic about 10%, and here we have 50% effect. Next slide.
5 minutes, please. 5 minutes. Thank you.
Sure, I will be in time. On this slide, you see the impact of dust on the Red Sea. It is upper slide shows radiative forcing of dust as a function of time, day of year, and blue shows shortwave forcing. And you see that in the middle of the year, in summer, forcing reaches 60 watt per meter squared, cooling. So it is counteracted by long wave warming, the yellow line from aerosol layer, but total forcing reaches 40 watt per meter squared, strong cooling of the Red Sea. And this cooling from our simulations so causes cooling of the SST by ½ degree and decreases the evaporation from the Red Sea by 10 centimeters. No, this is interesting that in this case, dust forcing also affects the intensity of overtoning circulation, but in this case, it slows down the overtoning circulation. And to summarize, next slide, please. So the Middle East regional climate sensitivity is significantly higher than average over the globe. Regional warming depends on the emissions scenario, but in the worst case could exceed 5 Kelvin in the Central Arabian Peninsula by the end of the 21st century. The special distribution of predicted warming indicates the important role of regional seas. Coupled WRF-ROMS regional ocean atmosphere model is a proper tool to tackle the Middle East regional climate. It calculates exceptionally well the impact of Pinatubo and dust radiative forcing on the Middle East. So it's important to use observed Pinatubo case. So it allows us to evaluate how well model could produce observed events. Dust-induced regional radiative forcing develops an important climatological impact on the surface air temperature, sea surface temperature, and sea circulation, and has to be incorporated in the predictive models. At least for Middle East, where the radiative forcing of dust is very significant. The changes in the atmospheric circulation patterns associated with the phase of Arctic oscillation, Indian monsoon, Atlantic SST, position of ITCZ and ENSA contribute to regional sensitivity of the Middle East climate and produce even stronger climate signature than direct radiative forcing. Internal seas, Red Sea, Arabian Gulf, and Mediterranean Sea are affected by global warming and have to be included interactively in the regional climate forecast for this region. Thank you.
Thank you very much, Professor Stenchiko, for this very interesting overview of the coupling, this coupled picture over and around the Arabian Peninsula between atmosphere and the ocean. I can see one question coming, and maybe we can have another one. So the question is, one criticism on climate models is that models exaggerate volcanic cooling, like Pinatubo. Do you agree?
Not in our model. So there are many reasons. This should be considered more accurately. So model produce different radiative, there are different radiative forcing. So we have to be sure that so input is restricted, and we know well how much aerosol was in atmosphere. And the second, it is climate sensitivity of different models. So we, in our simulation, we can pretty well reproduce the magnitude of the response. Recently, so I saw that many up-to-date models overestimate stratospheric heating, for example. Pinatubo is very important case study that could let us better understand mechanisms and test the models. And here I just want to mention there are two important climatological observations that could be used for this. One of them is cooling of the surface, and the second is warming of stratosphere. So you cannot exaggerate, say, amount of aerosol because you overheat stratosphere. So this very, very important to put this in perspective and look at picture altogether. So models, many models produce so erroneous results because of input data or representation of size distribution of aerosols. But so that's current progress. Yes. And in some cases, at least in our work, we were able to produce the results comparable with observations.
Professor Stenchikov, can I add another question by Jos Leriveld? Have you also looked at the Arabian Gulf? What would you expect there from dust radiative forcing?
Radiative forcing of Arabian Gulf is probably larger than over the Red Sea. For the Red Sea, interesting so observation is that the forcing is very non-uniformly distributed. So in summer, we have much stronger forcing in southern Red Sea that affects overtoning and circulation in the sea. Arabian Gulf is covered by dust more uniformly, and optical depths of dust even higher than over Red Sea. So I expect that effect on the Arabian Gulf even stronger than over Red Sea.
Okay. So I think because we are over our time, I would like to thank Professor Stenchikov and actually all the speaker of this oral session, and I'm waiting instructions from the control center.
Thank you.
Yes. Thank you very much. Thank you, Professor Stenchikov. Our warm apologies once again for the technicalities. In fact, our apologies also to you, the chair of the climate modeling and prediction session, Professor Hadjinikolaou. It was a bit of an unfortunate session in terms of technicalities, but still a very diverse one and of course extremely interesting one as we have just heard. Unfortunately, technicalities have taken their toll on the duration of this session. However, we are not extremely way beyond our time. But what I will do now is I will invite you only for a short breather instead of a coffee break. So let us be back in 3 to 5 minutes. In fact, I will say from now, let us be back at 4:12 exactly, 4:12 okay. Cyprus time for the virtual poster sessions. So let's all be back in 4 minutes so that we manage to recuperate some time. Thank you, Professor Hadjinikolaou. Thank you all. Be back in 4 minutes for the virtual posters presentation. Thank you.
Did
Okay, dear colleagues, so I hope you've had a short breather. I do apologize for the shortness. I would like to welcome you now to our virtual presentation, poster presentation session, which will work as follows. We centrally have the one sliders. I convey to all the participants that we now have a very interesting power speed session of virtual posters because we have 13 virtual posters, one sliders, and the presenters will have a maximum of 2 minutes only. So what we will do to save time and to be effective and get the full experience of this power speed poster presentation is that I will call out last names by the sequence of how we have scheduled the program, and then the presenters just open their camera and their mic and they go ahead, and I will time 2 minutes. The slides are changed centrally from dear colleague Andri Haralambous. So please excuse if I don't pronounce any last names correctly. Please feel free to correct me live. So without further ado, yes.
Without my intervention in presenting the authors, correct?
No. Just because we have scheduled it as a power speed mode, I would rather that we don't do it that way. I will just call out last names, and they are free to go for 2 minutes. Thank you, Professor Hadjinicolaou. So, Konstantinidou, please.
Hello, my name is Katiana Konstantinidou and I'm a postdoc research fellow here at the KRC. And today I will present to you our work on urban parameterization and high-resolution WRF simulations over the region of the Eastern Mediterranean and the Middle East. Urban heat island is a well-known effect of the urbanization, which characterizes urban areas with much higher temperatures than their rural surroundings. This study introduces the efforts made to simulate this effect over the EME region. Using the WRF model coupled with NOMP Landsat scheme and implementing the bulk urban parameterization, we perform an SSET simulation of 16 and 4 kilometer horizontal resolution for the summer of 2000. Here we show the preliminary results of one pair of stations of Ismailia, which is the urban one, and Port Said, which is the rural one. And the main points from these results are that the final resolution improves the representation of the urban areas. The temperature bias is over Ismailia
is plus or minus 2 degrees Celsius positive for WRF16 and negative for the WRF4, and over port side, slightly positive for the WRF16 and minus 8.3 degrees Celsius for WRF4. The simulated urban heat island ranges from 3 to 7 degrees Celsius, while the observed one is 0.1 degrees Celsius, with a 4-kilometer simulation to give the highest one, as it is also shown in the summer average diurnal cycle graph. Further, we are considering more pairs of stations to evaluate our simulations. We are planning to change the properties of the bulk urban parameterization to better represent our area of interest. And in the future, we want to utilize more elaborate urban schemes for our simulations. Thank you for your attention.
Thank you, Katiana, perfectly on time. Georgia Lazoglu.
Hello, can you see me? Okay, my name is Georgia Lazoglu and I'm a postdoc researcher at the KRC. Today I will present my study entitled Thin Copula Bias Correction of Model Daily Maximum Temperature in the MENA region. The aim of our study is the minimization of the biases, the systematic errors between the maximum temperature simulated by a global and regional climate models based on ERA5 reanalysis data. So we are using the ERA5 data as a reference data set for bias correction, and the data for target for bias correction provided by the HADEM3 global climate model and the WRF regional climate model. The area of study is the MENA Cortex domain, and we are the new of this study that we are using a recently introduced statistical method, the Thin Copula method for bias correction, which is a combination of triangular regular networks and copulas. The advantage of this method is that it's focusing on the marginal distribution of the parameters that we are trying to find their correlation. So in the images, you can see the maximum seasonal air temperature according to the ERA5 data, and the biases between the model and the ERA5 data before and after the bias correction. Additionally, you can see the statistical analysis with 3 types of plots: QQ plots, violin plots, and density plots. The results shows that after the bias correction, the biases between the ERA5 data and the simulated data have been minimized significantly. So we propose this method, the Thin Copula method, for bias correction, as it has the ability to increase the accuracy of the simulated data during all season in most of the studied area, independently from the topographical features, the magnitude of the initial biases, and the used model. Thank you very much for your attention.
Thank you, Georgia, and apologies, it was Lazoglu, not Lazoglu. So, Kyriakidis, please.
Hello, everyone. So I'm Pantelis Kyriakidis. I'm a PhD candidate, and I will be presenting the impact of assimilating Aeolus remote sensing wind data on regional Aeolian dust, the case study of October 2020. So the launch of the Aeolus Wind LiDAR mission by the European Space Agency provides wind data that include Rayleigh clear and Mike cloudy winds that are assimilated into the ECMWF IFS data. To test the added value of the satellite wind data, 2 simulations, one with and one without the Aeolus data, were carried out over the Eastern Mediterranean and Middle East region using the WRF Chem model for both spring and autumn of 2020. From now on, in our analysis, the assimilated data set will be referred to as HEL4 and the control one as HEL1. So figure 1 shows that comparing observations from MEP to simulated dust concentrations, the model performance remains unaffected by the wind assimilation in the spring period. This is not the case in autumn, where the assimilated fields that are shown in green outperform the control ones, which are depicted in yellow. And these instances have been highlighted with the blue boxes. The improved performance is also seen from several statistical metrics in figure 2, which is a result of comparison with air and aerosol optical depth observations. It can be observed that there is a reduction of overestimation model outliers and a more symmetric distribution. So specifically in a 2-week period in October, there are significant differences between the 2 simulations, and it's been verified by other stations that are not shown on these slides. So the simulation differences are seen in figure 3, where simulated data appears to have more stagnant conditions over Middle East, leading to higher dust concentrations, which are in better agreement with observed concentrations. The assimilation wind profiles of Aeolus significantly influence the vertical distribution of the dust layers, also shown in Figure 4, and further assessment will be done with lighter observations. To conclude, there is potential improvement in the model's performance regarding meteorological conditions, which in turn affect other components such as dust mobilization, which is the focus of this study. Thank you very much.
Thank you, right on time. Thank you, Pantelis. So Hassan, please, from EMA Egypt.
I'm with you. Hello.
Please, go ahead.
Good afternoon. I'm Rukai Hassan. I'm a meteorologist at Alexandria International Airport. Aim of my research is the assessment of reanalysis data sets against radiosonde observation over Eastern Mediterranean. First, we try to find an alternative source of sounding observation data because there is a lack in their numbers comparable to surface stations. So we choose 9 stations with different climatology and compared 4 variables: geopotential height, temperature, dew point temperature, and relative humidity from 2 data sets, ERA 5 and ERA interim, with radiosonde observation at 4 different isobaric levels through the period 2000-2017 by using Pearson correlation, mean bias, root mean square error, and Telom diagram. Second, we study the relation between upper air temperature and North Atlantic oscillation using Spearman correlation. The result we got, both reanalysis data showed a strong correlation at all levels except dew point temperature and relative humidity at upper troposphere. The figure on the top right, the Taylor diagram of temperature at 4 levels, shows that temperature from both reanalysis are generally consistent with observation, as well as geopotential height. But dew point temperature and relative humidity has a small bias and increased with altitude. The figure in the left corner shows the root mean square error of relative humidity for both reanalysis and how it increased upward. We got a negative relationship between North Atlantic oscillation and temperature at lower troposphere and positive relationship at 200 hectopascal. My conclusion that ERA 5 is slightly better than ERA interim and could compensate the radiosonde for geopotential height and temperature, and dew point temperature and relative humidity need more study at upper atmosphere. Thank you.
Thank you very, very much. Perfectly on time. I would like to invite, please,
Thank you.
Christodoulou. Aliki Christodoulou, please.
Hello. Good afternoon, everyone. I'm Aliki Christodoulou, and I'm a PhD student at the Cyprus Institute and IMT North Dwe. Here I'm presenting you the first near-time characterization of fine particulate matter and volatile organic compounds in Cairo. This was a campaign that took place at the premises of National Research Center in Cairo in a suburban site. Cairo is, has a complex environment since it sources from desert, city center, emissions, and also agricultural activities. In total, we have placed 15 online and offline instruments at the National Research Center. And overall, we observed quite extremely high concentrations for both fine particulate matter and VOCs, which is compared to other extremely polluted megacities in the world, such as New Delhi. The quality assurance has been done through the comparison of offline and online dataset. You can see in the middle for individual species with really good correlations. Then the analysis of the offline analysis from filters showed some dust episodes in the fine particulate mode. On the top right, you can see the mean mass concentrations for the main submicron aerosol components. The major component here is the organics, followed by chloride and ammonium, which it's unusual high for such areas, and also 2 extreme pollution episodes are detected, reaching to masses up to 350 microgram per cubic meter. Last but not least, I present you some selected VOC species on the bottom right. where aromatics and alkanes range between 2 to 10 micrograms per cubic meter, and I have specified some of them that are coming from fossil fuel emissions such as toluene and xylene, and also biomass burning combustion from benzene. Future work includes source apportionment studies using positive matter characterization in order to investigate the sources of these extremely high levels of fine particulate matter and VOCs. Thank you very much.
Thank you, Eliki. I would like to kindly remind to all to please keep your cameras and your microphones closed unless you are presenting. So please switch off your cameras, anyone who is not presenting now. Moving on to Liakakou, please. Mrs. Eleni Liakakou.
Hello, I am Eleni Liakakou, Senior Researcher at the National Observatory of Athens. In the slide, you will find some highlights of our non-methane hydrocarbon measurements in two sites with contrasted characteristics in the greater Athens area over the period 2015 to 2019. The first measurements took place on 2015 until 2017 in the Athens, in an urban background site in Athens, close to the historical center of the city. Based on the PMF results, 5 factors were identified and quantified, with traffic-related emissions being the most important for the contribution on the levels of VOCs. By included in the runs results from heavier volatile organic compounds and alpha-pinene. We can separate the wood burning fraction from the regional background, whereas the most important finding was that we found that anthropogenic sources like fuel exhaust, wood burning, and gas use were contributed to the levels of alpha-pinene, a compound which is typically considered as a biogenic one. Currently, during 2019, the measurements also with automatic gas chromatographs with 30 minutes resolution was repeated on urban coastal area close to Piraeus port. Here, the characteristics of the site is completely different, and we have impact from shipping and industry. This was obvious on the profile of the source apportionment, with fugitive emissions being the most important and accounted more than 75% and increasing during summer. Here, traffic and the diesel-related emissions contributed almost equal to the levels of non-methane hydrocarbons. The traffic was mainly responsible for the levels of alpha-pinene. To close the short presentation, it is important to combine this type of measurements with results obtained by ACSM in order to have an idea about the role of reactive organic species such as the monoterpenes on the formation of secondary organic aerosols. And for Athens, we estimated the contribution of 22 and 13% respectively for summer and winter. Thank you.
Thank you very much. Dimitriou, please. Mr. Konstantinos Dimitriou.
Can you see me?
Yes, please go ahead.
Dear colleagues, good afternoon. In this work, we used the recently developed 3D version of concentration-weighted trajectory model in order to identify not only the spatial, but also the vertical distribution of air flows associated with high levels of fine and ultra-fine PM constituents in the Eastern Mediterranean basin. Therefore, we used the advanced 3D concentration-weighted trajectory model in 3 distinct altitudinal layers above ground level. These are shown at the lower left side of our slide, combined with PM10 and PM1 constituent concentrations obtained from the Agia Marina Xiliatou rural background superstation situated on the island of Cyprus. High levels of secondary inorganic aerosols such as sulfates and ammonium were associated with eastern airflows from the Middle East in all layers during cold period, whereas during warm period, when the so-called Tethesian winds prevail in the Eastern Mediterranean basin, Northern flows through Turkey also have a strong impact. Therefore, emissions of an anthropogenic origin in all those areas seem to play a major role. Similar findings were also indicated for potassium due to biomass burning. However, PM1 bound potassium contributions were more strongly originated from continental areas during both seasons, whereas additional crustal and marine potassium contributions were revealed for coarser particles. Dust intrusions from Northeast Africa and the Middle East triggering episodes of calcium and metals were identified mainly in layer 1 and were more intense during cold period, whilst higher contributions of elemental carbon were detected during cold seasons due to the enhancement of coal and oil combustion and were associated with eastern air flows from the Middle East in layers 1 and 2. All our findings were in good agreement with the results of a principal component analysis revealing major sources of aerosols in Cyprus. Thank you very much for your attention.
Thank you very much, Mr. Dimitriou. The floor to Mr. Kaskautis. Dimitris, we cannot hear you. I'm sorry.
Okay. Okay, now?
Now it's okay.
Because
please.
Yes,
Thank you.
By the organizer also. So in this work, we investigate the optical properties and the curvature effect in spectral scattering and absorption coefficients for key identified aerosol types in Athens. The curvature effect, let me explain that when we present the aerosol spectral scattering or absorption or spectral optical depth in logarithmic coordinates, it does not go to a linear regression as per the theory, but there is a curvature on these calculations, on this representation in logarithmic coordinates. So using a SIM with absorption angstrom exponent versus scattering angstrom exponent, we identified some basic aerosol types in Greece, in Athens, like black carbon dominated, the mixing of black carbon with brown carbon, poor brown carbon, large particles and dust mixed, etc. And then we took into consideration 2 specific months, December 2017, which was a very turbid month in view of residential wood burning emissions, and March 2018, which was a very dusty month in Greece and in the Eastern Mediterranean as well. So in these 2 specific months, we took the identified aerosol types and presented them in logarithmic coordinates and examined the curvature effect. And we have seen that if we have a lot of black carbon aerosols from fossil fuel emissions mostly, this spectral curvature approaches to linearity. If we have more dust or more coated black carbon with brown carbon, or with dust or poor brown carbon conditions from enhanced residential wood burning, then the curvature in scattering and in absorption as well enhances, and we also show about the signal of this curvature, if it is positive and negative, representing convex or concave type curves respectively. This recently published work.
10 seconds, Dimitris, please. 10 seconds, wrap up.
Yes, and this one we need some more data for the scattering coefficient mostly, in order to justify our first results.
Thank you very much. Proceeding to Georgoulias, please.
Sorry. It seems that this is the wrong camera, but it is okay as soon as you can hear me.
But we can hear you, Aristidis, so please go ahead.
Okay, let's go on. Let's go on. Sorry for that. I will present you a couple of key results from our recent paper in Remote Sensing Journal. Actually, we developed a radiative transfer system that makes use of high-resolution satellite data and climatology data, and the well-established SP-DART radiative transfer model, which we further developed so as it can take into account the UVB's absorption, and also to separate between tropospheric and stratospheric NO2. On a climatological basis, it seems that the liquid clouds dominate their effect on the surface solar radiation, with an effect of minus 36 watts per square meter, and ice clouds follow along with aerosols with minus 19 watts per square meter, and aerosols with minus 13 watts per square meter. And the radiative effect of tropospheric NO2 is smaller by 2 orders of magnitude, which is nearly negligible. Under clear skies, the radiative effect of aerosols is 3 to 4 times larger than for liquid and ice cloud covered skies, while the radiative effect of NO2 doubles, but it's still negligible in the area. Thank you for your attention.
Thank you very much. Next to Germain Piolen. I apologize if I have not pronounced well.
Hello everyone, I'm a PhD student at KRC, and so I will talk about methane and non-methane hydrocarbons. So as you know, methane is a greenhouse gas that is a major climate forcing, but nevertheless, the sources of methane remain too poorly known. And light alkanes such as ethane are co-emitted by fossil fuels activities like oil and gas exploitations, and are promising traces for understanding methane emissions associated with these activities. So through a combination of new measurements and modeling, I try to better assess methane emission in a region. The objective is therefore to improve estimates of local and regional anthropogenic methane sources using combined methane measurements using a picaro and non-methane hydrocarbon using 2 gas chromatographs. And for this, I am currently building an innovative data set in February of 2021. I'm showing here only an example of 1 week, but several months of joint data have already been acquired at the Cyprus Institute. I wish to obtain a representative signal of long-range transports at the regional scale, in addition to a local one. I study this dataset and start to use backward trajectory simulations to identify the origin of the air masses inducing the observed concentrations, and I try to investigate the possible implications of 1 or more co-emitting sources of methane and ethane, such as oil and gas production platforms in the Eastern Mediterranean. And as Stratos said this morning, a near source measurements campaign in relation to oil and gas operation in the Middle East as part of the MCARE project is also planned in Qatar in 2022, with the aim to improve again the estimations of methane emissions in the Yemen region. Thank you for your attention.
Thank you very much. So moving on to Mohammad. I hope I have pronounced well.
So this is my first name. My name is Rumi.
Oh, apologies. So Rumi, okay.
Yeah, don't worry. So good afternoon. So I want to present you briefly what we are doing at the Accelerator Laboratory of the Lebanese Atomic Energy Commission. So our contribution to characterize effectively chemical elements of atmospheric particulate matter, in particular PM2.5, and to investigate potential source apportionment in this regard. So we are using nuclear analytical techniques or ion beam analysis techniques, in particular proton-induced X-ray emission, which we can determine with this technique element from sodium and above till lead. Not only that, we have developed the necessary protocol to also with other ion beam analysis techniques to determine total carbon, and we have also the necessary tool to determine black carbon, so we can include or deduce organic carbon in this way, but it is still under development as research only. So we have the necessary sampler to sample simultaneously PM2.5 and PM10, but we put more attention on the sampling of PM2.5. So it is important to develop the necessary infrastructure in our lab to be able to contribute effectively to this kind of research. So we have also the assistance and the help of the International Atomic Energy Agency in Vienna. So we are studying this project within a regional aspect. So we are part of what it is called Eurasia country. So it is the Arab country in West Asia. About 7 countries are participating in this project. So we have done an extensive sampling between 2016 and 2020. Unfortunately, with the COVID and other reasons that I will not tell you here. So just to share just few results concerning the dust storm that was happened in 2015. So
10
we
seconds,
can
please,
have,
to wrap up.
excuse me?
10-15 seconds to wrap up, please.
Yes. So this is some few results that I want to share with you. Maybe the time is not enough to develop. So thank you.
Yes, thank you very much. I now have M. Zanati. Floor is yours, please.
Antonio Zanatti seems to be offline, so we move on to the next and last presentation.
Okay. Thank you for that. Then I have Salah, Zainab Salah, please. The floor is yours. Zainab, we see you, but we cannot hear you. Still not hearing you. I think you're actually also paused. I do not see a development here. Andri, is the sound coming from you or is it from Zainab?
It's from Zainab, but her microphone is, she's not muted. So I don't know what's happening.
She's not muted. Zainab, you are not muted, but we cannot hear you. So maybe another. Well, we hear that you are. Maybe switch off your webcam and let's try to see if that that will allow the sound perhaps to come through better. Because I also see your webcam frozen, so perhaps it will be better for the connection if you switch off your camera and you try to speak. No, I still cannot hear anything. Do we perhaps have, Andri, do you see if Nagla Zanati is online?
Okay, can you hear me now?
Yes, Zainab, is that you? We can hear you. Yes, please, go
Okay.
ahead.
Nagla is also online, so we can see her presentation after.
After Zainab. Let's not lose Zainab now that we have her. Please, Zainab, take the floor.
Okay. Okay. I'm Zainab Salah from Egyptian Meteorological Authority. My presentation is about calculate an indicator to represent what happened for the dust storm with the IPCC scenario. We used the CDO software to calculate the maximum daily dust concentration from the output of the regional climate model of RegCM4 at every grade point within the region of Egypt. I calculated over the North Africa, the MENA region or the MENA region, but I focus only on Egypt. After that, I take the time series of the maximum daily concentrations during the reference period from 1986 to 2005, and then these reference periods were used to define the thresholds corresponding to the dust concentration. Normal dusty days is represent the percentile 75. High dusty days is 90 percentile. Very high dusty days is 95 percentile, and very and extremely high dusty days is 99 percentile. Then this percentile used to calculate the percentage of occurrence of the different categories of dusty days up to 2010. As you see from these figures, figure A is the reference period, is the percentage of normal dusty days in the year. From this average from 1986 to 2005. And figure B is a chart, is the difference in the period from 2021 to 2040. And this for RCB 4.5, and the C is the difference between the RCB 8.5 and reference period. And the next down chart is for percentage of very high dusty days. As you see from these figures, the percentage of normal dusty days.
10 seconds
Okay.
wrap up.
Okay, the percentage of dusty days, normal and very high dusty days, it increased by very from 2 to 4 percent. Thank you.
Thank you very much. Thanks also for the understanding of the time. Can we go back to slides, please, Andri, to exactly. Please, Nagla Zanati, the floor is yours.
I'm here. Can you hear me?
Yes, if you can do it just a little bit louder, it would be great, but we can hear you.
Okay, I'm sorry for this technical issue. My name is Nagla Zanati. I'm a researcher at the National Authority for Remote Sensing and Space Sciences. I will present that atmospheric aerosols pollution in Egypt. This research is aims to study the aerosol pollution over Egypt and the characteristics, radiative and physical characteristics of aerosols over Egypt, as particle pollution is one of the high streets of pollution facing the country. In this study, I have used multiple satellite data such as MODIS and OMI with the AeroNet ground-based observations in order to achieve this purpose. As you can see in these slides, the changes in aerosol optical depths during the period from 2012 to 2019 by analysis of the AOD, during this period, I have noticed that the aerosol pollution in Egypt is bimodal. It increases in spring and also in autumn. In spring, we can see that the natural dust storm is coming from the Western Desert, as presented in this slide. This is this example of a dust storm observed in May 2018. This natural dust storms result increase aerosol loading. Also in fall or autumn, the human activities or anthropogenic aerosols plays a great role in increasing the aerosol pollution in Egypt. One of the main activities is biomass burning. As we can see that there is a high number of fire incidents over the Nile Delta, which is a huge agricultural zone in Egypt, and farmers are doing this activity of biomass burning, which increases the aerosol pollution during fall. By the analysis of angstrom exponent climatology, we can confirm that in spring, the fine mode fraction of the fine mode particles are the
10
common.
seconds wrap up, please. 10 seconds wrap up.
Okay. In autumn, the coarse mode particles are the common source. By doing the validation between AeroNet and the MODIS data, there was a correlation coefficient of 0.76. Thanks for your attention and sorry for the technical issue.
Thank you very much. We have managed to complete with this presentation the 13 virtual posters. With that, I would like to announce to all participants, all panelists, and all chairs that we have managed to conclude this first day of our workshop. If you have seen, I have placed on the chat an announcement for just later after this first day of workshop. We have a continuation, but targeting a Greek-speaking audience and Greek speakers. However, it is relevant to our work. It is about atmosphere pollution and climate change impacts on our life and health. This is co-developed and co-presented by 3 EU-funded projects and Norwegian funds project, the EMECare, Accept, and IQServe. I apologize, IQServe is a nationally funded project. So very interesting presentation as well. I have shared the link for that, but it is targeting a Greek-speaking audience. However, you are more than welcome to join and to listen to the results of those 3 projects as well. Now, having that said, just to recap, today we have had a busy day. We have heard about atmospheric modeling and prediction, air pollution and impacts, atmospheric dust, climate modeling and prediction, and we have had an interesting power speed session with virtual posters, 13 of them. We have 8 more of them tomorrow, but they will be relating to climate change and weather extremes. So 8 more virtual posters tomorrow at the end of tomorrow's second and last day of the workshop. More importantly, the sessions tomorrow will begin at 9:30 Cyprus time. So 9:30, we would like to welcome you all back tomorrow to hear about climate change and weather extremes. This will be a session chaired by Professor Jos Lelyfeld. Then to hear about greenhouse gases and remote sensing, a session chaired by Professor Michalis Vrekousis. Then a session on new instrumentation chaired by Dr. Anne Meiser. Then a session on education and training opportunities chaired by the head of our graduate school office, Dr. Thesanthia Leondiou. So, having said that, 9:30 to Cyprus time tomorrow, on behalf of the EMECare coordinator and director of the Climate and Atmosphere Research Center of Excellence, Professor Jean Siar, I'd like to thank you all for your presence and participation today. Great thanks to all the speakers and all the panelists and participants. And of course, our warm thanks to the people who have made this technically possible. Angelos Alexandrou from our Cyprus Institute IT, and of course, colleagues Andrei Haralambous and Marina Papageorgiou. On behalf of Professor Sciar, we look forward to virtually meeting you again here tomorrow at 9:30 Cyprus time. Thank you all very much. See you tomorrow.
Thank you.